So I just started recording. Good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome my mathematical brother, Frédéric LATRÉMOLIÈRE from the University of Denver, and he will tell us how we can put together non-commutative metric geometry with non-commutative spectral geometry. So finite dimensional approximations of spectral triples on quantum tori. Frédéric, the floor is yours. Take it away.
Thank you very, very much, Piotr, and thank you for all of you to attend this nice Zoom seminar. While I've been teaching on Zoom for about a year now, I still am pretty fresh to Zoom seminars. I'm having a crash course with 4 of those in a row. So I hope it's going to be well. Please do ask me questions. I tell that to my students, it doesn't do much, but during the talk, please don't hesitate to interrupt. So indeed, as Piotr mentioned, my goal is to describe a little bit. We good?
Yeah, go ahead.
Sorry, my goal is to discuss a little bit how to put a geometry on the space of quantum spaces. So to give maybe some context or some externally generic reasons why I would want to do this, I think. It's motivated in part by mathematical physics, and I owe all of this, of course, to Mark Riffle's original work, and itself owes, of course, to Anaconda original work. But some of the reasons you may be interested in putting a geometry on a space of spaces is something like, for instance, quantum gravitation, which nobody knows what it is. I'm aware, but one of the ideas that I've showed up here and there and occasionally is maybe you want to put a geometry on the space of spacetimes, and I want to allow myself to work with quantum spacetimes as well. Another reason is that you will find in the literature in mathematical physics statements to the effect of some model, some physical theory, as say a quantum field theory or something, is in fact a limit of finite dimensional models, in particular of field theory on matrix algebras. Why you would want to use matrix algebras as a classical space here can be justified in many ways, and one of them is that it may preserve certain symmetries. Symmetries are somewhat fundamental in particle physics, and you can't really hope to talk about an action of SU2 on a set of n points. I mean, there are ways to prove measures and probably something like that, but if you have an n by n matrices, suddenly the symmetries of SU2, SU3, SL3, 1, etc., could be at least in principle preserved. So it's interesting to ask, could we indeed do physics at the matrix level and take a limit? And the question becomes, what does that mean to take a limit? And even from a system algebraic perspective, I'm hoping that this eventually might prove helpful. For instance, there are theorems that I won't talk too much about today, but within the framework of the subject I'm going to discuss, where you have a sequence of system algebras carrying some nice actions of nice groups, themselves metric. The whole thing may be Cauchy for a certain metric, and it has a limit, and that limit still carries a nice group action. So you have possibly constructions of new group actions, or the study of all other characteristic modules, etc. Using metric techniques could be interesting, maybe in the spirit of what people do also in Riemannian geometry when they use Gromov distance. So these are just very generic motivations, but just to say that, in fact, you do find in the literature various situations where people talk about approximating something, a torus, a sphere, a quantum torus, you name it, by matrix algebras. That would be, for instance, one example of what the framework I'm trying to devise here is useful for. So as Piotr said, and I didn't share my slide with Piotr, so he exactly said that sentence more or less, I guess, a very good approximation of the sentence. The idea is to bring together metric geometry. In particular, I'm thinking, Gromov-Hausdorff distance in Riemannian geometry with non-commutative geometry, by which indeed we can mean today non-commutative spectral geometry for constructing this geometry on the space of quantum spaces. And given my audience, this is something I probably should have removed, but I will argue to great risk that maybe at first approximation, because it's of course much more complicated than that, you could say that non-commutative geometry often proposes to study certain non-commutative generalizations of algebras of smooth functions over geometric spaces where smooth and geometric are context dependent. The reason I put that is to say that the focus of this talk in particular will be to study non-commutative generalization of algebras of Lipschitz functions. over metric spaces. So this is maybe a picture that is helpful when our slides get technical to keep in mind. I'm studying some non-commutative generalization of algebras of Lipschitz functions. Those will be called quantum compact metric spaces. So the specific approach that I'm going to take here is, of course, started as I'm going to do it by Mark Riffel in the late 90s. But of course, Mark in turn grounded his work in Anaconda's observation, I believe in 1989, that you could recover the metric of a Riemannian manifold using its natural spectral triple, and more generally, given a spectral triple, you can have a metric on the state space. And then I think, the context that I will talk about will not only apply to spectral triple, although as the title of the talk suggests, this will be our focus eventually. The motivations from mathematical physics are explained in various papers, and I gave you a couple of ideas. Certainly when I was a PhD student, a paper of Anaconda, Douglas and Schwartz was one of the papers that I read at the time long ago, and what inspired some of my work in this topic. And really what I'm going to do for the next hour and 20 minutes is to discuss various generalization of the Gromov-Hausdorff distance. This will be sort of the game I'm going to play today. So that's our plan. So let me start maybe actually talking about mathematics now. So what do I mean by quantum compact metric space? I find it useful to explain first the classical picture in one slide to give us a starting point. So if you take a compact metric space and you want to encode the metric M at the level of the C-star algebra C of X, then the natural object maybe to look at would be the Lipschitz seminorm, thus defined, as we all know. I'm allowing it to take the value infinity. And what you can do with this Lipschitz seminorm, among many things, is to take a look at sort of its dual seminorm appropriately defined. And in particular, it gives you a distance by duality on the state space of C of X, space of random probability measures of X. This is a fairly well-known formula. It is known under many names: Kantorov metric, the Wasserstein metric, the Lipschitz metric, the Earth mover metric, and in the case where we will work with spectral triples in about half an hour, or so the cone metric in that specific case. It's different because in one, the cone metric is in non-commutative setup. This is the classical setup. So this metric was introduced in the study of the Monge transportation problem, but it has since, found a little bit of life in probability and statistics in fractal theory. It has some nice properties, and I will give you some of the nice properties on the next slide. But it is worth noticing immediately that it makes the natural map that to a point of the space associate the Dirac point measure at X an isometry in the case where X is compact. So that tells you that you recover the metric from the Lipschitz seminorm. It is a good place to start a non-commutative description of metric spaces. And for the compact ones. So what I'm going to do now is I'm going to list certain properties of the seminorm L as a seminorm of a C-star algebra, which I would claim distinguishes the Lipschitz seminorm, say, from others. So it's not a complete duality. It's more like let's retain enough properties of the Lipschitz seminorm for the non-commutative setup so that we can do a nice theory without putting too many properties so that they are nice examples. The compromise that seems to emerge is the following idea. So the term compact quantum metric space is due to Anaconda, Dr. Kohn, and the list of axioms, grown, as I say, Mark added something. I'll explain that, and then we carried on the Leibniz properties as well. So it's been a bit of an interesting evolution, but it's not too bad. So quantum compact metric space is a pair of a unital C-star algebra, which is going to describe the continuous function on the space, but now I don't assume A is abelian anymore, so just a unital C-star algebra, and an analog of a Lipschitz seminorm, which will be a seminorm defined on a dense subspace. Technically, I'm going to ask it to be closed under the Jordan and the Lie product, which is only a dense subspace of the self-adjoint part of the C-star algebra for technical reasons I'll be happy to get to later. And then it has some properties of the Lipschitz seminorm. So for instance, 0 only on the constants, which translates in my non-commutative setup as 0 only on the scalar multiple of the unit. And the property that Mark added, so to speak, is that we want the naturally associated Kantorov metric, which looks exactly like on the previous slide, to induce a weak star topology on the state space. So this is indeed a property of the Morse control metric in the classical picture, which loudly justifies its applications to, as I say, various fields of mathematics. So that's the point 4 here in my definition is the sort of the crux point, the main point. However, if you look at 1, 2, 3, and 4, you will notice that there is no need really for system algebra for those 4 points, except, well, yeah, 2, 3, and 4, namely that the multiplication structure does not play any role. This would make sense in a much wider setting where you replace the self-adjoint part of a system algebra by any order unit space. That could make sense of point 2, 3, and 4, which is in fact the setup in which Mark started working. But for my purpose, I do want to work with system algebras. I like system algebra. So I sort of have put some emphasis in my work to stay within the category of system algebras for all the constructions to test some benefits that I may mention in passing later on. To do so, I require a connection between my Lipschitz semi-norm and the multiplicative structure. And since I'm working with self-adjoint element, I'm taking the I'm going to apply the L semi-norm to the real part of the product and the imaginary part of the product, known as the respectively Jordan product and Lie product. This is what my A composed with B and curly brace AB represent, respectively. And I'm going to ask that these are bounded above by an expression that here I use the usual Leibniz expression. This is what we'll get when L comes from a spectral triple. This is, of course, a property, a well-known property of the Lipschitz semi-norm as well. I should say that in general, I do not force that particular form of a Leibniz identity. There are situations when it is helpful to relax it somewhat. At the end of the day, some nice expression, say for instance, I mean, there are some precise assumptions on F, but they're very minimal. So like say some algebraic expression on A in those 4 variables will do the trick just fine. What's important at the end of the day is you choose one Leibniz property. That's what I call this 0.5 that suits your examples, and you fix it for the rest of your work for all the construction I'm going to make. So you have to fix this once and for all for a family of examples you wish. But other than that, it's a fairly minor constraint. And in this talk, most of them will satisfy, in fact, this particular well-known one. So that's a connection between the C-star algebraic structure and the sort of quantum metric structure. One last technical point that I must put for completeness, but which is really nothing to lose too much sleep about, is that I'm going to ask my analog of the Lipschitz semi-norm to be lower semi-continuous. This is for free in the Lipschitz semi-norm because it's a supremum continuous function where the variable is a function itself. However, this is a technical requirement. You could dispense with 6 to the cost of making the theory a little uglier, but the result would sort of be the same. But they would be stated in a less pleasant way, much less pleasant way. So I think it is a nice convenience because it does not eliminate any example. If you have a semi-norm that satisfies 1, 2, 3, 4, and 5, then you have one that satisfies 1 to 6, and which gives you the same Morse control metric by duality. So there is not much of a gain to drop 0.6. We don't get new examples when we make the theory less pleasant. So it's a technicality. So I call this a Lipschitz semi-norm or L semi-norm for short when I talk fast. And this pairs are quantum compact metric spaces. And in particular, they include C of X comma L, where X is a compact metric space and L is a Lipschitz semi-norm associated to an actual metric on M. But they include also some non-commutative examples.
Frederick, please forgive me. I know that I asked you this question at each talk that you give at my seminar, but could you remind us, please, this A circle B and this sort of Poisson-like bracket, what they mean? Because I think you didn't mention it.
A circle B is a Jordan product, so it's a real part of the product of A and B, so AB plus BA over 2. And the curly braces is a Lie product, so it's the imaginary part of the product, which is AB minus BA over 2I. Okay. So just to stay within the self-adjoint space, since I do not require L to be defined on the all of the system algebra. Okay. Since the theory is concerned, yeah, that's a comment. Since the theory is concerned with the state space, you know, it's sort of normal. The self-adjoint element are a bit emphasized in this construction. There are actually subtleties in general. With spectral triple, this won't be something to worry about. So you could actually, I'll show you how to define L, but many of you already know how to define L from the spectral triple, obviously. And in that case, you know, it's defined densely on the system algebra, and you could just have L A times B, and it implies that is less than whatever bound. So, but that's the general definition. Okay. And as I was no problem. As I was saying, there are in fact examples This is a non-exhaustive list I keep adding to every now and then, just to show that from 98 to last year, or maybe now 2 years ago, there's been various examples that have arisen, and quite of different nature, from nice metrics coming from algebraic action of compact metric group to various C-star group algebra. So the example that I listed, Ozawa Riffle, Chris Riffle, and I guess I had to remove one from Mark, sorry, Mark, if he's in attendance, but these are on group C-star algebras for discrete groups using actually a spectral triple introduced in that paper I keep mentioning from Anaconda from the 89, multiplication by a length function given a word length function. And yeah, so these are nice examples and of a different nature. AF algebras, I started with my students Conrad, and then Conrad has taken off this trajectory and extended our result to a wider class of AF algebras, etc. So there are a lot of good examples, at least, and in different flavors. So it's lately talking about Conrad and Jeskad, and I'm terribly sorry to mispronounce the name, proved that the published spheres with a natural spectral triple fit the context. Typically, where the difficulty is the proof that the Monge-Controvich metric induces a weak star topology. Mark has a nice criterion that everybody uses for that purpose, but it's still where most of the work goes. Okay, so later on in this talk, and I structure it so that I can actually get to the meat of the matter, I will show you some new examples about spectral triple in greater detail. But right now, I'm going to experiment a little bit. And instead of spending 20 minutes on an example, I would like to discuss a little bit more how I'm going to make sense of convergent symmetric spaces, then convergent symmetric spaces, staying at that level of abstraction, so that I don't clutter your brain with too many definitions and examples and notations. So often this gets a bit overwhelming. So what's nice about the category, the class of compact quantum metric space, is that it actually forms a category. It's a little remark in passing, but we have a nice notion of Lipschitz morphisms. They are basically whatever you want them to be within my context. So for instance, a natural idea is that since the state spaces, that's one of the sort of nice thing about quantum compact metric spaces, their state spaces are actually compact quantum metric, compact metric spaces, actually is the usual thing. So you could ask for a Lipschitz morphism to get a star morphism whose transpose map becomes Lipschitz between the state spaces as metric spaces. Or you could naturally ask that a sort of continuity, essentially, between the L seminorms in addition to continuity between the usual norm, comes free from the star morphism property. Or you could ask something interesting too, which is just preserving the domain of this Lipschitz seminorm, which that is preserving the Lipschitz functions, to speak in a generic. These are non-commuter objects, but that's the analog. And it turns out these three notions are equivalent within our setup, so that's kind of nice. By the way, this domain of L of A and L of B, this element in the domain of a Lipschitz seminorm, because of my lower semi-continuity assumption, they actually are Banach spaces for a natural norm. They are literally the analogs of Lipschitz algebras, but in non-commutative geometry. So maps between them automatically basically are Lipschitz. And so that forms a nice category. It's very easy to check. It's on it. I just wanted to point that out. You could, in fact, use that to define a Lipschitz distance between quantum compact metric space, but of course, it's very limited since it only is finite between star isomorphic system algebras. So it's not necessarily what we're looking for. What we're looking for is generalizing Gromov-Hausdorff, and to do that, what I'm going to need is a notion of isometry. In any case, the notion of isometry is also useful for me to tell you what I mean by two quantum compact metric spaces to be essentially the same, isomorphic. To introduce the notion of a quantum isometry, I remind you of this little result due to McChain, little in size, but quite useful and important. It says that if you have a subspace X of a metric space Z, and you have a function on that subspace, and says the function is Lipschitz, to make things simple, you can extend it to all of X. Every extension, of course, will grow the Lipschitz constant, but there is at least one that actually keeps it the same. But that is only valid if your function is real valued. If a function is complex valued or anything else, in general, this does not hold. There is constant, that is the best constant. It's actually a whole industry, or used to be, by varying the codomain. Here, I'm just going to take real value. It is a sort of a posteriori justification to work with self-adjoint elements in your system algebra is to mimic this property. So if you look at this property, it characterizes isometries in two steps. First, instead of a subspace into a metric space, you can look at the isometric image of the space into a subspace. So that gives you a necessary condition for a map to be an isometry, that you must be able to do this sort of lifting. And second of all, it actually tells you that, well, if you formalize it as a functional analysis, it says that the Lipschitz seminorm on C of Z, with my notation here, is the quotient of the Lipschitz seminorm. Sorry, I start. Yes, I start again. The Lipschitz seminorm on X is a quotient of the Lipschitz seminorm of Z. I flipped my letter. Contravariantly. So the same idea is what Mark Ripple proposed we use as a definition of quantum isometry, since it works indeed quite fine. It says that a quantum isometry is a star epimorphism, so surjective star morphism from UC star algebra A to UC star algebra B, such that the Lipschitz seminorm on B, L sub B, is the quotient of the Lipschitz seminorm on A. That's what this blue box says. And that's my notion of quantum isometry. And I should say, I think it's written here, that indeed, if you transpose this map and look at the map that it induces from the state space of B, with the Morse control rich metric for LB, to the state space of A, for the Morse control rich metric for L of A, then it becomes an isometry proper. And then what is a full quantum isometry? That's going to be my notion of isomorphism. It's basically a map that's a quantum isometries both ways. And when you put that together, you get a star isomorphism, which preserves our Lipschitz seminorm. So it's two quantum compact matrices, metric spaces are the same in that strong sense that everything is preserved by a star isomorphism. So now we have a category, we have our objects, and we know what it means for them to be the same. And now what I want to do with these things is to tell you what it means for them to converge to each other, to put a distance on the space of these quantum compact metric spaces I have just described. Again, same pattern as I've done for the first 10 minutes or 12 minutes. I'm going to define, to tell you, to remind you in one slide of the classical picture I am attempting to generalize. So in Riemannian geometry, it actually started in geometric group theory, but right now I think it's particularly popular, but I may be wrong in Riemannian geometry. There is this object called the Gromov-Hausdorff distance, which is an intrinsic version of the Hausdorff distance. What I mean is, you give me two metric spaces, compact metric spaces, they float around, two manifolds or something like that. And they are floating around, they don't have any, they're intrinsically given, right, as topological spaces with a manifold structure, and they have a metric. And I would like to know how far apart they are. Now, if they actually were sitting inside of a nice metric space, you embedded them into R to the 2n+1 or something for X and Y being of dimension n, then you could take the Hausdorff distance between them. But that's not intrinsic, obviously. So what Gromov proposes, well, do that for every possible way you could possibly embed X and Y into a compact metric space. And just a compact metric space, so Z can be quite wild. So you embed X and Y isometrically in an arbitrary metric space. You take the Hausdorff distance between the isometric copies of X and Y, and then you remove the dependency on the embedding by taking the infimum of all those possible embeddings. That gives you a real number. I suppose it could have been 0 all along, but it isn't. It turns out that this thing is actually a metric up to isometry, by which I mean it is 0 if and only if the two metric spaces are isometric, fully isometric. And it's complete, and it's a nice, well-behaved metric, which, as I say, received a lot of attention in classical geometry, maybe a little bit less in non-trivial geometry to my detriment, but this is the object I am going to try and generalize. So,
do you remember what was original motivation of Misha Gromov?
Yes,
to introduce?
Certainly. So from Gromov, my understanding is, so the Gromov 81 paper is a publication of the IHES paper where he was looking at this theorem about, virtually nilpotent groups, and it's the connection between nilpotency or virtual nilpotency and polynomial growth of the groups, right? So this was applied to the Kelly graph. And so it's interesting, there's a bit of a history in that. I'll take that as an opportunity for my tangent. Actually, this definition I just gave you, which is a commonly stated definition of the Gromov-Hausdorff distance nowadays, if you look at a standard book on the topic or article on the topic, is not how Gromov introduced it. So Gromov actually introduced a more general metric for locally compact, in fact, for metric spaces, but I guess it's well behaved in particular for complete proper metric spaces. That's where things work nicely. So more general than just compact. And the definition is slightly more involved, but since I'm going to work in the compact context, I will use this topological recurrent metric, which, as I say, is commonly used, in say, Riemann geometry. This exact metric, however, was described by Edwards someone named Edwards in 1975, and his motivation was actually closer to my first slide. Namely, he was interested in trying to metrize a space of spacetimes to carry out some of the program of Wheeler and geometrical dynamics. So it turns out the paper of Edwards fell into, was forgotten, and the first quote he ever had was actually in one of my papers when I stumbled across it. But it's interesting because the formula everybody uses is actually straight in the paper of Edwards, and the metric Gromov introduces is more general than that, and is not the one people use when they do compact stuff. It is the one they use when they work with locally compact manifolds. The idea is similar, but it's more technical to write. So does that cover your question, Piotr?
Yes, thank you very much. Yes, this was a very nice detour. Thank you.
So this is the object we would like to find an analog in non-commutative geometry for. And there is a long history about that, which I selfishly must skip for time reasons. But the first analog of this was due to Mark, of course, in 2000, 2001, whatever, publication delays notwithstanding. This first analog was at the level, as I discussed, Mark was working with order unit spaces rather than C-star algebras. And it turns out that going from a metric where distance 0 is well behaved as far as order unit spaces are concerned, but not so good as far as C-star algebras are concerned, was not a trivial problem to solve. And there were many different proposals about which way one could go. And I'm going to rather selfishly discuss about the proposal I made, which I will let people better placed than me to discuss that, but seems to be actually the one that works quite well. And there are reasons for it that I will try to it's not just because it looks pretty, it's because it turns out that by specifically restricting myself to the category of C-star algebras, I can talk about modules, group actions, etc. Over C-star algebras, I can use the C-star algebraic framework for my work, which is important for what I'm going to talk about today. Whereas for some other constructions that might be tricky, like say if you look on operator system and completely positive maps, theory of modules may be a little more, I'm not saying it's impossible to do, far from that, but I'm just saying obviously it's maybe a less natural object. So in order to stay, I like to kind of stay within my natural objects here on purpose, I'm going to explain to you how to do a form of the Gromov-Hausdorff distance, which due to the long history of different variations on the theme, I had to find a new name for. I came to this later. And so, there was already a whole bunch of, there was quantum Gromov-Hausdorff, non-commutative Gromov-Hausdorff, completely positive Gromov-Hausdorff, etc., etc. So I decided that I was going to use a different word than distance, and proximity was already taken by Mark. In fact, my metric sort of fixes a problem with something Mark called the proximity, but wasn't quite satisfactory. And here it is, it's called the propinquity, which is more or less a synonym actually in English for proximity. People always ask me. So the dual Gromov-Hausdorff propinquity is my non-commutative analog. How do I do that? First, I mimic Gromov idea. So the Gromov idea is you want to know how far two quantum compact metric spaces are. So those are A and B in my picture here. A and B are fixed. I want to know how far they are. And to do so, the idea is, well, first you embed them into a third quantum compact metric space, arbitrary. So that's my D up there. That's the third one you embed into. Of course, contravariance, as we are well. The story between C-star algebra is kind of contravariant to the story between spaces. So here my embeddings are, the arrows look backward, but that's the direct analog, of course. And by pi's here are quantum isometries in the sense I defined. So this is an isometric embedding. In fact, it does give me an isometric embedding between the state spaces in the usual Gromov way, but it is more restrictive because pi and pi have more properties in it. They remember the algebra. Every time you do that, you want to give a number to that structure. I call that a tunnel. Again, the vocabulary has evolved over 10 years. And so the idea is to associate a number to this. And the number should be the Hausdorff distance between things. That's kind of mimicking our construction. So the natural guess is you have the state space of A and the state space of B living inside the state space of D by being mapped by the transpose of by A and by B. And as I said, these transpose maps are isometries. So we literally have an isometric copy of the two state spaces of A and B into that third metric space, the state space of that third metric space. So you could guess that you take the Hausdorff distance between those. This is what basically, I mean, okay, this would be natural, but it is a little bit more difficult. I mean, it's a little trickier. That's not difficult, it's just you have to take the right estimate. The right estimate, it turns out, is this one, where you take the Hausdorff distance between the state space of A and the whole of the state space of D. So this doesn't show up in classical picture, because in the classical picture, you have things like you can restrict functions, you can truncate function, and all sort of simple tricks, which eliminate, you can always take D of the same form, basically, and it's a continuous function, a disjoint union of the spectrum of A, the spectrum of B. So in the classical picture, you could restrict a little bit what D looks like, and the picture gets a little easier. But in the quantum cases, you can't really, these operations of truncation and so on that you would use do not behave well or are not even defined. And so in general, or don't behave well with respect to the Lipschitz seminar. So that's slight modified version is the one that works. And of course it bounds what you would guess by the triangular inequality, but it is better. So, okay, cool, that's the extent of a tunnel. That's a number associated to one embedding. And it's my analog of taking the Hausdorff distance between the spaces, albeit it's different, right? It's between state spaces, etc. And then, well, you follow the prescription, you take the infimum of these numbers over all possible tunnels of that form. The F in front of tunnels in my slide is just a reminder that all the Ds that you choose should have a Leibniz property, the LD should have the same Leibniz property, or weaker, than LA and LB, or stronger, I wanted to say. So LD has the same Leibniz property in particular as LA and LB. So that's a detail, just for those of you who maybe are more familiar with the thing, but it's important that we restrict ourselves to one fixed Leibniz property. If this is not uniform, then you won't get the right properties. But that's just a parenthesis, and I will never mention that again. So this is fairly similar to Gromov construction at this point. And it, you could ask, does it work? And it does. It turns out that this construction does give you a complete metric up to full quantum isometry between compact metric spaces. That's the first good news. So complete mean, every Cauchy sequence of compact quantum metric space for this thing have a limit defined up to that notion of full quantum isometry, which I'll remind you of down here because it's important. So I mean, some of the work here, if it's where the history of the field kind of matters a tiny bit, in the sense that Mach distance, if you apply it to this setup, the construction is similar but different. But anyway, you would get distance 0 if and only if there's a order star isomorphism, order unit isomorphism to be specific, between the self-adjoint part with the same property down there. But you would not necessarily get a star isomorphism. And since not every system algebra is isomorphic to its opposite or stuff like that, it means that it's not actually necessarily a star isomorphism. It doesn't lift necessarily to a star isomorphism. So this was actually a challenge to make it so, I would argue. And certainly Mark can if he's around. I'm sorry, I do not, as usual, see who is here and who is not. So I'm working on some assumption here, but certainly he can confirm or if I'm correct or if I'm lying about that.
I'm here.
You are here. Yes, I see you now. I scrolled through my pictures a little bit. So, so this is sort of our distance of choice. So, okay, so phi is complete, and for up to full quantum isometry is good, but there's another metric that does that. It's discrete one, right? So, I mean, okay, is there more to that story? Did we get a trivial metric? And no, it's not trivial, at least in the following sense, but there's more to it. But at a minimum, it also has a nice property, and when you restrict it to the class of objects of the form C of X Lipschitz, seminorm, actual Lipschitz seminorm coming from an actual metric on X, then you recover the metric, the topology, sorry, of the Gromov-Hausdorff distance. So by that, I mean, you have a map which to a compact metric take X with a metric, associates C of X with a Lipschitz seminorm. This map becomes an homeomorphism from the Gromov-Hausdorff distance topology to the topology induced by the metric I just wrote. That's the way to phrase it technically. And that's very nice. So we really did generalize the idea of grammophiles of distance. The metric itself are different, okay, but the topologies they induce are the same. So yeah, that's a picture. So there is a continuum of spaces in there. It's not a trivial metric either. It's not discrete. But of course, what about non-commutative examples? So again, I will give you some new ones toward the end of the talks once I explain everything. But here's a list of past examples, not all of them from Spectral Triple, of things that work. So for instance, the first bullet point is kind of relevant to later today. There is a metric introduced by Mark on quantum tori and fuzzy tori using the dual action of respectively the torus and the subgroup of the finite subgroup of the torus, appropriately chosen. And you can use that to put a metric on these fuzzy tori, which are certain type of matrix algebras. Well, technically, they could be the n by n matrix algebras, and on the quantum torus. And then there is a way to prove that indeed for this very natural matrix, the fuzzy tori converge to the quantum tori. And there is no irrationality condition or anything. So this is quite general, and it gives you a whole lot of continuum too, because the family of quantum torus, of quantum tori, sorry, is continuous as well in their natural parameter you use to twist your ZD. So in the co-cycle, it's continuous in the two co-cycles you use to twist ZD to get your quantum torus. So this is there's a continuum there in the non-commutative side of things here. So that's a non-trivial metric. That's already, and that was in fact one of the original motivation I had one of the first. That's my kind of workhorse example, I will confess. But Mark, has used this metric to prove that you can also get full matrix algebra approximation, so approximation of continuous functions on technically co-adjoint orbit of semi-simple Lie groups by full matrix algebras, using that metric by endowing the various algebras with natural quantum metrics. In the case of that comes from the action of the semi-simple Lie group. So the example I wrote here, which I guess is the motivating example, is the continuous function of the two-sphere can be approximated by full matrix algebras where all the quantum metrics come simply by the action of SU2. Well, S2 is a quotient of SU2, so that's one. And then the full matrix algebra, all of them carry an entire action of SU2, an ergodic action of SU2. And that is an example of where working with full matrix algebras allow you to preserve some symmetries all along, rather than improving, if you want, on finite approximation of the sphere by finitely many points where symmetries would be broken. So Mark, of course, proved this convergence first for his metric a while ago, but this particular 15 years of date refers to the strengthening of the original convergence to the stronger metric I just proposed. Okay, and then there are other examples. I mean, I mentioned F algebras. With my students, we have various interesting example of fun, well-known families of F algebras like UHF, of course, but also F Roshen, etc., that form continuous families. He has some nice connection in another paper that I didn't mention about felt topologies in the F context and convergence of sister algebras in form a metric, and there are other examples. I will point out that I do not know what the closure of the finite dimensional quantum complex metric spaces are for my metric. It's something I haven't solved, but I do know that it contains a lot of things. It contains all the nuclear quasi-diagonal sister algebras and that with quantum metrics. So that's the last point here. And there are more examples. This is just a list, but to give you that this is a non-trivial metric. Yes? We good? No questions so far?
No, I think this is just random background noise.
Yes, I know. I just like to do that because, as I say, when I teach, you never know. And I apologize if it's repetitive, but it's Zoomness and my lack of habit with it. Okay, so there are examples of convergence that are interesting for this interesting metric. So now, here we come at last to it's not too soon, right, to the main idea. But I feel like I need to give you this background. I don't think that my constructions is well known by any means. So certainly it's worth detailing how it works. And it's the metric construction is actually the cornerstone of the rest of what I do. Everything else is built on top of what I haven't defined. So what I want to do now is talk about convergence, not just of quantum compact metric spaces, but of actual spectral triples on them. So I'm going to try to explain what I mean, but this is the goal of what we're going to focus on. So first, what is a spectral triple? So I've had the question many times, and so I believe, but I may am wrong, that in this paper of 1989, I mentioned, and Anaconda did actually define the concept of spectral triple. I think it's the first time. Don't want to say something wrong here, since Alan is in the audience, but so
No,
of course,
no,
I'm happy to be corrected.
Sure. No, I mean, you should know, in fact, I already had it in my inaugural talk in the Collège de France, which was in 85.
Oh.
So, I mean, it's
Okay, so I should put it 85. Yeah, I'm happy to, because I mean, I don't know the first thing. Was it the first time in print, or is there a paper before that
well, yeah,
I
I
missed,
think, well,
which is quite common?
yeah, but I mean, in print, certainly, yes, yeah, probably, yeah, sure.
Okay, so 85. So anyway, this is the idea of.
I have a question. What kind of an
Yes.
algebra? You have this A. Oh, you
Yes.
say you want that to be
Yes.
a unital C-star algebra? You want A to
Yes,
be a
so
unital?
thank you. That's right. Yeah. Thank you for this good question. So yes, so this does require some discussion. So the definition of a spectral triple is I believe that there is some variation, so to speak, in the following sense. That may be specific. There is a core set of requirements, which is actually usually longer than the 0.123 here, and then there are usually, things that you want, like that I will mention in passing in a moment. But what I'm going to talk for this particular talk, I'm going to take the core, sort of the intersection of what is agreed upon to be a spectral triple, and because that's all I need. I mean, most importantly, I want to take a minimal set of assumptions. I can define a distance on object of that form, which includes everything that people will more commonly call a spectral triple. And Dr. Bohm pointed out right now that in addition, I'm going to take a little bit of a change in the usual thing, but it's a free change. I'll explain what I mean about the definition. So a spectral triple is a triple consisting of typically some sort of star algebra of operators on a Hilbert space. So your A would be a bunch of bounded operators on a Hilbert space. H is your Hilbert space. And then you have an operator that is supposed to be a Dirac type, well, a generalization, an analog of a Dirac type operator in the case of manifolds. So what I do here is I close my star algebras. Okay, I just take the norm closure and I do a C-star algebra, but then you'll see there's a little A1 in 0.3, and the little A1 in 0.3 will be what people would typically put as the first algebra here. Instead of A, they would put what I call A1 or something inside of A1. But for me, because of the connection with compact quantum metric spaces, it is much more convenient to deal with the C-star algebra. If you see, because if you remember my definition of a compact metric space, I did the same thing. I work with a C-star algebra and a densely defined semi-norm on it. It's more convenient. I'm going to play the same game here. My spectral triple is really, of course, what should be the smooth element, so to speak, is a dense subalgebra of A rather than A, as is commonly used. I apologize for the departure with the common terminology, but it will prove helpful so that I don't have to repeat, sort of text closure, etc., etc.
D is an unbounded self-adjoint operator. Is that correct?
That's right. So I think I forgot to write dense domain. The domain should be dense. It's not written.
Well,
it
yes,
should have been.
okay.
Yeah, that's what's missing. Thank you. So indeed, you have a unital C-star algebra. You have a Hilbert space on which A acts, and I will usually write A as if it's directly on, inside of B of H instead of just represented. And my operator D is a self-adjoint, densely defined. That's the word dense is missing here. Densely defined self-adjoint operator with compact resolvent. And such that if you take the elements in your C-star algebra, which preserve the domain of D, I can define a commutator with the, that commutator has bounded closure. This algebra is dense. So this is my sort of the analog of the C1 elements, right? If you were not in classical geometry. The example that we have to keep in mind here is A would be the continuous function on, say, a very nice compact, connected compact spin manifold, connected for what I'm going to do next. H would be, square integrable sections of the spinor bundle, the canonical spinor bundle in that case, and D would be the standard Atiyah type Dirac operator. But this framework is more general, right? And so usually people will add things to this that I will not talk much about in this talk. time being one of the issue. For instance, you can add a grading if you want to start talking about, let's say, the index of D with respect to that grading. That's a very, for some spectral triples, those are the even ones. You can ask a real structure, and that's also an important tool. And they have typically order conditions, first order, second order conditions, which have to do with what the analog of differential forms commuting with the original algebra for the first order one. And then you have also condition on the asymptotic behavior. That's maybe the most important of the spectral of the operator D. So the spectral, the asymptotic behavior of the spectrum of D is the resource upon which spectral geometry is built. And so by generalization to non-Euclidean geometry, the spectrum of D is essential, right? Especially asymptotic behavior to define all sort of nice objects. So this of course is very important, but I'm going to take a slightly different route. I mean, we have in the audience many people who are infinitely, literally more expert than I am on this. My interest is on the metric aspect of things. So this is actually what I'm going to work with. So it's sort of a minimal set of assumptions. Okay? As Anaconda observed, we can use this data to define an extended metric, a pseudo-metric on the state space, and using a formula that is now known as a cone metric associated to the spectral triple. And we recognize that suddenly it would fit naturally our framework as a Monge-Kontorovich metric for a particular choice of Lipschitz semi-norm, the norm of the commutator. But for me to do anything with this, and that's different from an interesting question, I want this metric to induce a weak star topology on the state space, right? That is how I connect this structure to what I talked about for the first half of the talk. And this is not trivial, it turns out. Certainly with assumption 1, 2, 3 alone, there are examples. I believe there is one that from Putnam, for instance, I think it's even on a commutative system, where this fails to be the case. So this is not this is an actual requirement, and it's a bit of a mystery to me exactly what additional properties of spectral triples commonly used would imply this. Certainly, Anaconda's reconstruction theorem suggests that if you make a list in the A is abelian, and you have a long list of properties where you identify essentially a particular smooth subalgebras of your system algebra A here, and have certain nice properties, existence of a cocycle property, etc. Then suddenly you recover actually the usual Dirac operator on a nice manifold. So in that case, this red box would be satisfied for free. So somewhere along the way there is this property holds, but I don't, for me it's just going to be, I'm afraid, just an assumption I must add, because I don't really understand what operator theoretic, what I guess I'm saying is I don't know what operator theoretic properties on D I must have for this definition to hold. However, a lot of the examples we work with, in fact, all of the examples in my green box, obviously, that I just passed, and the few ones I'm going to show you today at the end, all of those do satisfy this property. So it's common, but it's not systematic. So a metric spectral triple, for lack of a better word, is a spectral triple in that very simplified sense, for which when you do this LD being the norm of the commutator on the dense algebra, you get a common compact metric space. In other words, the cone metric induces a weak star topology. So those are the objects I want to put a metric, the distance between. Okay?
So this boxed equation is the defined definition of LD, right?
That's right.
Okay.
That's right. Yeah. So if you put LD to be that, then, and that's the notation I'm going to commonly use, hopefully.
You didn't write a column, this is why I'm asking.
Yes, I didn't write in Pascal, I wrote in C, I'm sorry. I'm sorry, yeah. Sorry for that, yes. That's a good point. So, all right, so what are the ingredients I'm going to use to define my convergence? Well, one we already saw. So we have a metric. So at a bare minimum, we can discuss about the convergence of the underlying cone metric. That's perfectly fine. And that's in fact done in some of the examples I already mentioned. Then I'm going to look at kind of functional analytic ingredients. So I'm taking a road that I hope will be entertaining by being kind of different from what...
Andrzej Sitasz is asking a question. I could see his hand raised. Andrzej, go ahead.
So maybe I wait till the end. So this is, since Frédéric already passed on to the next thing, so maybe I wait till the end. So please go on, Frédéric.
Okay, sorry, I saw your hand raised. So
okay. Sorry, yes. Thank you, Piotr, for pointing this out. Same with the chat. I have not acquired the reflex to check all of this stuff.
It's difficult to lecture and to answer the chat. That's difficult.
That's right. Yes, that's proven to be tricky. So, okay, so the object I'm going to use are very functional and analytic in nature. Okay, so what I'm interested in is to try to define a distance between this object that preserve not just isometric, but the entire structure in a way that I hope will make sense when I get to that theorem. I mean, make a distance on between spectral triples so that the distance is 0 when they are literally unitarily equivalent in a sense I will make clear in a few slides. So the ingredients I'm going to use is first, well, there's a natural object, the graph norm of your Dirac operator. It gives you, I call that a sub-OLS space. It's a bit of a, maybe of a stretch, but it has a result similar to a sub-OLS embedding result. So I think it's fair. It's a Hilbert space. And it has this sub-OLS embedding type result. So that's given by the graph norm. So I have a new norm, which we will see in a moment, shares a lot of the properties with Lipschitz semi-norm. So it's a very natural object for me to look at. But it won't be enough. I'll tell you what happens if you only take the 2 first ingredients. If you want a good metric on spectral triples, one suggestion I offer is to also consider the natural flow, unitary flow given by the Dirac operator. This is a very natural action because it turns out that in my research, in between, you know, what I've talked about, which is back from 2013, and what I will talk about today, which is in the rest of the talk, which is the spectral triple, which is now. In between, I look at the covariant property of the Bronner-Hausdorff metric. And so it was very natural for me to look at group actions as a way to carry information about spectral triple. But also think if you're looking at it from a physical perspective, and I mean it in a very generic way here, but it's looking at the quantum dynamics, right? Exponential of 2i pi t times.
You know, this group is extremely important because it has finite propagation speed. In other words, if you look at space, not space-time, and if you take this group, you get something which doesn't go faster than the speed of light.
Okay.
Transform a function which has a given support into a function whose support doesn't increase faster than the speed of light. So I mean, it's a very, very useful one-parameter group.
Yes, thank you very much. And so in my, sort of naive way to understand it, those are the right object, but at least those are natural, I should have said, natural objects to look at. I believe also, and Anaconda might be able to tell us more about this, that this object has to do with the geodesic flow as well. It is not the geodesic flow, but it is related.
No, the geodesic flow is with absolute of D, the absolute value of D.
With the absolute value, here you go. Okay, thank you. Thank you. The one is absolute. So it's a natural geometric object, but as a functional analysis, that's also like what you do, you have a self-adjoint operator, you sort of exponentiate it, give you a group. That's a very natural reflex to look at this subject. So those are the 3 ingredients. I need to tell you not only how to make the metric close, but also how to make those 2 additional ingredients close. What does that mean? What does that mean? All right, so first, let's look at this graph norm, which actually is kind of the more complicated thing to write notation-wise, even though I don't think it's. Anyway. So, okay, so you could look at a spectral triple as a special example of a module, of a Hilbert module. And well, it's a Hilbert space. It's actually, I'm going to talk about them as C-star correspondences in a minute, which may look like overkill, but it's the right setup for what I'm going to do. And if you look at your D norm, the graph norm, so I'm going to call them D norm, just I had L semi-norms, I have D norms, it's quicker. These Dirac norms, these D norms, sorry, these graph norms, they have a property. If you look at, that is for free. I put in the theorem metric spectral triple, but actually this is for any spectral triple with my simplified definition. The unit ball of this thing is compact. That's your sub-OLS embedding, sub-OLS embedding result. And that's because of the compact result, and it's not too hard.
Yeah.
And it has a sort of,
sorry. Yeah, please.
And it has a sort of Leibniz relation, right? Given by this expression down here that if you multiply a vector by an operator, apply an operator vector, you get a Leibniz-like relation. It doesn't matter the exact form. What matters is that we recover a pattern we were familiar with before using Lipschitz semi-norm. So same thing, but instead of a Lipschitz semi-norm now, you took about the graph norm of a Dirac of an operator, but it turns out to have similar properties. So you could look at, it's a simplification, but again, a good one to look at this set of vectors whose D norm is less or equal to 1 as a sort of like your state space. It's a bit of a lie, but it's a heuristic, which may be convenient for a talk. I mean, after all, in some sense, they are states, right? Because, okay, I'll leave it at that. So, okay, so that means that in fact, if you abstract a little bit, and I need to abstract it, it's not just for the luxury of it, it is useful. If I abstract a little bit the data that I have, I'm going to put it at the bottom of my slide. I should have put it on top. At the bottom of the slide, if I take a spectral triple, I'm going to make a package information that I'm talking about as follows. There's a Hilbert space. There is the D norm, that's the DD thing. That's a graph norm. Then C0 is just a placeholder for the time being. It's complex numbers with a zero semi-norm on it. And then I have my A, which acts on H, and the associated quantum metric that comes from the Dirac operator, and then the norm of the commutator. So you look at this package of data, what properties does that satisfy, which I'm going to abstract? And I'll tell you really quickly why I want to abstract it in a few slides. Okay? So I'm going to call a metrical, I changed the name 3 times as I go along, a metrical C-star correspondence, in part because I was wrong and I put left action twice instead of right. Anyway, cleaning things up, you get a metrical C-star correspondence is an object like that with a Hilbert module or right Hilbert module M over B. So in the case of Hilbert space, it's H is over C. That's what my C is for, which also carries a left action from a C-star algebra A, the left and right action commute, A act by joinable operators, etc. Such that you have, on each of the quantum metric, on each of the C-star algebra involved, you have a quantum metric, because I'm really working with Lipschitz algebras in these guys here. And on top of it, I want this D norm to have the same sort of properties as the graph norm of my spectral of my Dirac operator, but abstracted. So, if you look at what my D norm is, it's densely defined again. It's bigger than the norm because, well, the graph norm is defined like this. The reason why I have 0.1 is the replacement for the Lipschitz semi-norm is 0 if and only if your element is a constant, because that's not true, of course, when you work with the D norm, with connections and so on. You can have connections being 0 on things that are not constant. So to get rid, the replacement, so to speak, of that condition becomes that I just want to lower bound on my D norm, which is easy. You just take the max of whatever you're interested in the norm. The key properties too, that's the replacement for the Morse control-rich metric gives you the Weak-star topology. It becomes the state space is compact in the topology induced by the D norm, essentially. And the third one and fourth one, you don't have to worry about this H and this G. I just don't want to write an explicit formula, just as we had with compact quantum spaces. There's flexibility here. It's a detail. You want a reasonable connection between, say, taking the inner product of 2 elements of the Hilbert modules and then taking the Lipschitz semi-norm of that versus what's the D norm of those sections. And, those are Leibniz relations that come from natural properties. So I should say that this structure that I just described, it's in particular fits the QVB thing at the bottom here for a spectral triple. That's an example of such a structure, in which case B is just a complex numbers and Hilbert module is just a Hilbert space. But there are other examples of such structures, which comes from genuine connections, like the Heisenberg modules over the quantum tori with the natural Yang-Mills connection, for instance. That also fit that framework with appropriate definition of what the D norm is, but it's essentially an operator norm obtained from your connection. So there are other examples of this, but in this talk, I will focus on the spectral triples. However, I still do need the generality of Hilbert modules, and I hope to explain.
Sorry, Frederick, to interrupt you, but could you please decipher in point 3 the notation with this curly R and?
Yeah, sorry, you're right. Thank you, I forgot. Real part, imaginary part.
Okay, real and imaginary. Okay.
Because remember again, yes, again for the same reason that so that's just a technicality, but yes. And everybody asked me that, and I'm so naive because in LaTeX it's just /RE and /IM. So you'd think, but no, nobody knows this notation, including me. I need to remind myself. Just thank you very much. Yes, so it's just a technicality to make sure you end up in the self-adjoint part. There's the notation is nasty, but the concept is just you apply the Lipschitz semi-norm to the inner product and it should be well behaved. Except you can't.
And is it just my impression, or is your definition a tiny little bit asymmetric that you require?
Yes, no, it's not your impression. It's not an impression. Yes, it's real. It's correct. So your Hilbert module over 1.
Okay, exactly.
But you're only a module over the other. So that's a C-star correspondence, not a Hilbert. In fact, it's important, because usually you're not, and the Leibniz conditions, so 3 and 4, relate to each of the actions. So 3 is about which one? 3 is about the Hilbert module structure, and that's enough to carry everything. So just having 3 will make everything behave nicely relative to the right action, it turns out, using polarity identities and all that. So 3 is all I need to deal with the right action. 4 is what I need for the left action, to make sure that when I do my metric, it remembers something about the left action by just playing with norms. Because at the end of the day, you only play with norms, but you want somehow the multiplication to follow. So the linearity part is never a problem. The vector space structure is never a problem. But how do I keep the action going? How do I make sure that in my convergence, the actions will be the same if distance is 0, etc., etc.? This is what this point 3 and 4 are. And you're right, they are symmetric, absolutely. And in fact, in the case of Hilbert's spectral triple, violently so, because A, so the second part, the A part, is the algebra, okay, of your spectral triple, whereas B just becomes the complex numbers. There's almost nothing there. So you could ask me, why do we have to drag this complicated structure? I'm going to try to explain that now. So let me tell you what I'm going to do. What I'm going to do.
Did you just keep a formula in your last slide? Or this QVB?
No, that's a definition again. I see this is going to be a recurrent theme. So sorry, in Pascal, I would have, on Algol, I would have put a column before my equal.
And QVB stands for what? Quantum what?
Yeah, that's a good point. So that's the notation I use in the paper, and I apologize for that because I keep changing my terms. So I used to call those quantum vector bundle.
Okay.
But not the best. First of all, because I should put the word metric somewhere because it, obviously this is kind of the core idea. And then C-star correspondence, I decided it was a more common term because they're not just vector bundle, there's left and there's two actions. So, but that's what it meant. So I may, unfortunately I wrote a couple of papers with this and I haven't changed my notation yet. I probably will, but so sorry for that. But I'm going to use this quantum vector bundle associated with my thing, my spectral triple. So how do I define how close they are? So I'm going to take a diagram like this, call that a quantum embedding. So, we've seen that, right? I mean, this is a tunnel thing that I worked before. That's how I compute the distance between two quantum compact metric spaces, where as a slight derogation to make the slide vaguely readable, L1 and L2 correspond respectively to the Dirac operator D1 and D2. And I forgot a 2 on the second A, which is bad, but unfortunately I'm not on my screen. So there should be a A2, L2. I apologize for that. Okay, so that's what we were doing when we're trying to compute the distance between the compact quantum metric spaces A1, L1, and A2, L2, where L1 and L2 this time come from a spectral triple. We just embedded them into a third one and then did some things, okay? But first we did that. So, okay, I'm gonna do the same with modules. So how do I do that? Well, let's look at this diagram and let's start from the edges of the diagram. So you see H1, D1, and H2, D2. Those are the Hilbert space endowed with a graph norm of your Dirac operators, okay? And there's this ... to remind us that they're over the complex numbers as Hilbert modules. And then what I'm going to do is I'm going to do a diagram which is similar, but I'm going to have a Hilbert module this time, which surjects onto H1 and H2 in such a way, as written in this little note at the bottom, that the quotient norm of T via theta 1 is D1. And here theta 1 is just a linear map because, well, okay, no, it's a module map. Okay, so you have to be, by module, I mean, you have a change of the base ring, right? I mean, you go from C plus C in this picture to C. And so you want the obvious thing that theta 1 of a scalar, which is here in C plus C, multiplied by a vector is pi 1 of that scalar multiplied by theta 1 of that vector. Okay, that's what I mean. So the obvious definition. And so you want this diagram here with the additional property. And so, yeah, we good? Okay. I do not mind being interrupted at all, just so you know. So that's why I keep stopping if I hear noise, because it's totally fine with me in this Zoom thing. So if you look at this picture, it looks similar, right? I mean, there's two arrows because, well, we have to keep track of the module and the module over what. So this is why it's 2 stages, but other than that, it's pretty natural. So that would be a natural diagram. And because of the time, I won't discuss at length why suddenly I'm okay with ignoring the Mach chain thing and lifting sections instead of real valued functions isometrically, but there's a reason why this is actually a reasonable framework to have. It just would take a bit of time to explain. So you should look at this as a very analog construction. It's almost the same thing. Okay. And then I want to put them together. Okay, well, that's what it looks like. So when you put them together, you see at the bottom, I have my triangle with my C plus C surjecting on C and C. In the middle, I have my modules and my Hilbert spaces. And on top, I have the tunnel between L1 and L2, L2, right? So we're just putting them together. But the reason why I put them together is I want everything in there to sort of commute in an obvious way. So for instance, you have these theta maps between modules. And as we pointed out, These are modules on the right over C, on the left or C plus C, and on the left over A1, A2, or D. Well, you want the maps to theta 1 to be a morphism for both structures at once, right? Things like that. But if you have a diagram like this, every time you have a diagram like this, which is not that bad to find, then what I do is, well, I have at the top here a diagram between compact metric spaces, and at the bottom here another one between compact quantum metric spaces. That's where the mystery Q I have not mentioned come to play. This C, there is only one way to make C into a compact quantum metric space, is to put the seminorm 0. It is, after all, continuous function on one point. So there's not a whole lot you can do with a metric. So that's what you get. But on the other hand, C plus C, well, there are a few ways. I mean, they always look the same, right? They are constants times the difference between both components. That's what the Lipschitz seminorm will look like. Obviously, it's a continuous function with a 2-point set. So we know exactly what we're doing there. But you want it to be a quantum metric space. It's part of the data here, so that when I'm going to say that this structure converges, they say the structure given by a spectral triple converge, everything converges, not just, so including the base space. It might sound weird because it's 1 point, but what I'm saying is that you have 1 point, which is the complex numbers upon which H1 is defined. And then you have the other complex numbers, quote unquote, over which H2 is converged. Well, those are 2 points, and I just want to make them really, really close to each other in a 2-point space. But I can't just make them equal. That would be too easy. In general, they're just really, really close, and they are constrained on how close you can make them so that this diagram actually works. Remember, you have all sort of conditions. I mean, I'll go back real quick, but you have to have things like this Leibniz condition in particular, 0.3 and 0.4. If you make things really, really close, you're going to change the Leibniz condition. It's a fun exercise. So there's a lot of rigidity built in this diagram, it turns out, by asking all the maps to be, all the seminorm to quotient the right way, and all the maps to have the obvious algebraic relation. Every time you have that, what I do, so this is the definition here is a formal description of the picture before, and I don't want to go over this in detail. It's just a picture I just showed you. I define the extent again of that thing. I call it tunnel, but this time it's between metrical structures. And it's just the maximum of the tunnels of the extent between the quantum metric spaces. So it doesn't involve actually the module anymore. The rigidity of the diagram carries the modules for free. It's kind of nice. There is an estimate you can get on the state spaces of these unit balls of the D norms for free by just simply asking A1, how far is A1 and A2, and how far is C from C in this diagram, using that tunnel idea that I described before. So I don't need to tell you what the tunnel is, really, except it's a maximum of the tunnel of extent, of the distance between A1 and A2 and the complex numbers in this picture. And then I take the infimum of all of those, and I get actually a complete metric again. And it is 0 exactly when those C-star correspondences are exactly the same. So there's an isomorphism between them defined in whatever you would guess would be right, which preserves all the seminorms, the D norms and the L seminorms. Everything is preserved. So that works really nicely. Okay, that's a natural extension. And then you could ask me, okay, so you do that. You give me 2 spectral triples. You do this QVB construction. You associate to them an object in that category I just described. You take the distance that I just defined between them. What do you get? Well, you almost get what you want. You get that distance 0. It happens exactly when you do have quantum isometry, because it's built in between the compact quantum metric spaces that you obtain from your spectral triple. But on top of it, you almost conjugate the Dirac operators, but not quite. You conjugate their real part, the absolute value of them, or the square, whatever. So almost, this is what happens when you do the definition with modules. Is that so far? I mean, there's a lot of arrows, but the idea is really just here, you pile up 3 diagrams of the same exact shape, and you just ask for compatibilities, and it's really everything you would guess. There's no mystery there at the end of the day, except maybe that the quotient of T is D1 by theta 1. Quotient of T by theta 1 is D1, and same on the other side. And then you just go through a machine and you get a metric. So it's almost a metric on spectral triple, but not really. It's unsurprisingly maybe so far only conserve the metric properties of the spectral triple. So how do I go one step further and basically remove the square at the bottom here, so that distance 0 would mean actually there's a same. And of course I need to give you examples too, and it's coming hopefully. Piotr, by the way, it goes until
Say it again, what?
Time-wise, it goes until, I just want to make sure.
Yes, you have 21 minutes.
Yeah, perfect, that's what, yeah. Okay.
By the way, since you asked me a question, let me now retaliate and ask you a question. Have I missed it, or did you mention somewhere when talking about quantum vector bundles, the magic terms finitely generated projective module?
You did not miss it, and I do not need it.
Okay. Okay.
You did not miss it, and I do not need it. It is interesting. So if I had to guess, and it's a guess, okay, but it's let's say a semi-educated guess. Even if I took a sequence of finitely generated ones, I do not expect that in typically the limit would have to be, right? So it's good that I don't need it. The replacements, I mean, it's a terrible way to say it, but between friends, the replacement between math brothers secretly, right? This replacement is this compactness of the ball. It's not finite generation, but it does, the finiteness piece in my world is expressed in terms of compactness of certain spaces. It has nothing to do with finite generation, but there is a finiteness kind of condition, but it's completely different. It's phrased completely differently.
And your adjective modular propinquity derives from the word module, not the usual meaning of modular functions, whatever, right?
It derived from the word of module, as in a Hilbert module, okay, of the kind I've described. Mm-hmm. Yes. So so this was introduced before I talk about spectral triples. This was the first example, as I say, where Heisenberg of interest. You know, the first non-trivial example where Heisenberg modules of a quantum tori. Nothing to do with this picture. The same metric can be used for that. But here, this talk, I want to talk about spectral triples. So it applies nicely, and it is one of the ingredients of my notion of convergence. Does that cover it?
Yes. Thank you. Yes.
Sure. So one last ingredient. So I told you this is hard. So okay, this is how to handle the graph norm, right? I mean, you can see it in that slide. This is the second bullet point here. This is how we handle both at the same time, the quantum metric and sort of its analog at the level of the Dirac operator. Then how do I talk about the, how do I get the actual Dirac operator? And this is where the dynamics come to play. So I have this natural dynamic. I think I changed my convention from 2 pi ITD to ITD, and actually ITD is the one I use. So that was the other slide. The 2 pi was X pi. It doesn't matter usually, but typically I use this one. Anyway, point is, you have this action, and this action is automatically an action by isometry for your D norm. So it's isometry for the norm, unitaries on the Hilbert space, but also for the D norm. So it's a nice action, very well behaved. And how do I incorporate? So now you have a bunch of objects that converge, metric spaces, bundles. How do I incorporate the action on them converge? That's interesting intrinsically, right? I mean, you want to be able to say, it doesn't have to be just for this particular example. I mean, you have a group acting on a bunch of quantum metric spaces, you'd like to know if you can carry these actions to the limit, right? And that's, the answer is typically, yeah, you can say quite a few interesting things. So I'm gonna tell you how, and I don't expect you to remember all this definition. I just want to convince you that it's doable, and there are papers where this is expanded at length, but here is the idea. So first, if I want to talk about convergence of actions, I want to be able to talk about convergence of groups, right? Because that's the thing that's going to move as well. So it might sound weird because you might say, well, here's a group is R all the time. So what, I could just ignore that. Well, I'm going to need the ingredients on the same slide because in fact, you need a way, sure, you have two actions of R, but they don't have to go at the same speed or anything, right? So you need a way to adjust that and measure, if I adjust that, how much of an error do I make? Because ideally, you want them to, distance 0 means exactly the same. So distance not quite 0 means then you're made good to different speed, but not too tragically different. So how do I measure that? And second of all, anyway, the setup works for more generally. So there's no difference. I mean, technically, to work between arbitrary metric monoids actually versus just putting R. The definition would look essentially the same. There's not much of a gain. So you have two. It might actually be more confusing if all the groups are the same actually when you state it the first time. So you take two proper monoids, which here I agree will be R. Okay, fine. But in general, two metric monoids. So monoid, I mean, there's one operation, it has a semi-group and it has a unit. It doesn't even have to be a group, but you can look at that. Proper group. Proper means, it's another word is boundedly compact. So every closed bounded set is compact. So it's refinement on locally compact. And this is the right setup for everything to work nicely. And it's normal, it's a standard setup for Gromov-Hausdorff convergence. So those are normal spaces for a change. And this is another way you can do Gromov-Hausdorff convergence in classical picture. So it's a distraction. It gives you a metric that's, well, okay. You could use these ideas to define Gromov-Hausdorff convergence instead of using embeddings like I did at the beginning. It is convenient when working with groups to take this picture. So I call an epsilon isometric isomorphism. That's a terrible name, but I just didn't know how to name them. And in my papers, I typically say an iso because I don't want to repeat that every time. It's a pair of maps, and in general, they're just any functions. They don't even have to be measurable, though. Imagine in practice, they typically are, but any maps. One going from G1 to G2, one going from G2 to G1. So the base index of sigma 1 goes from G1 and sigma 2 goes from G2. Okay? And what is the idea? Well, they're almost an isometric isomorphism, which you could list what it means, right? So for instance, it means that if you take an element in G1, apply sigma 1, then apply sigma 2, so you return, the distance between where you started and when you return should be no more than epsilon. And you go on like this. It means that if you take two elements in G1, you multiply them and you apply sigma 1 to that, or you apply sigma 1 to each of them and multiply them in G2, the distance between those two things should not be more than epsilon. I mean, it's a standard idea, right? It turns out it's nice. You can compact all of those into an equivalent definition, which here you have, which is this blue box. All you have to do is this blue box, which looks a bit like an adjoint property, is equivalent to everything I said and more in terms of, you know, the distance between sigmas behave like isomorphism up to epsilon and well, like morphisms, group morphisms, monomorphism up to epsilon, and like inverse of each other up to epsilon. So the way it works is you have this condition where, you know, you take elements, you apply the map, so you product the element first and then apply the map, and you look at this condition. You don't want things to stay close to each other, but you don't want them to stay close on all of G1 and G2 in general, because G1 and G2 may not be compact. So in fact, here we're going to work with R. So you want that to be happening for a long time. The longer this equation holds, the better. So there is this epsilon that plays two roles. You want this equation, this inequality, to hold on the unit ball centered at the unit of radius 1 over epsilon, right? So the smaller epsilon is, the bigger the ball becomes. So that's a trade-off. So you call something that satisfies this inequality for a given epsilon an epsilon isometric isomorphism. Smaller epsilon means that your maps are closer to being isometric isomorphism on a larger ball centered on the unit of your monoid. And then you take the infimum of the epsilon for which you can find a map like that and define a metric. It turns out, again, complete. Well, actually, no. Okay. You define a metric up to isometric isomorphism on proper monoids. So distance 0 not only means there's a symmetric spaces, it means there's a same monoid. There's a monoid morphism coming out. So that's interesting. It dominates the pointed Gromov-Hausdorff distance pointed at the unit. It's also interesting to note that completeness is an interesting question. And essentially, short of it is completeness holds on classes where there's some sort of uniformity on the Lipschitz constant of the right multiplication, which is kind of an amusing statement. I mean, there's a paper on that. So for large classes, which includes all the abelian groups in particular, this is even a complete metric. So this is the Gromov-Hausdorff convergence for groups. And you know, if you were someone working in Gromov-Hausdorff topology, I'm sure this is something. I mean, I wrote it, you know, but and I look in the literature, and there are variation on the theme, not exactly this one, but variation on the theme. So I think everything you would come up with would be equivalent to that. It really is a natural idea. And once you have this is the worst slide of the talk, I promise. What you do is this horrible thing. So it looks horrible, but I'm going to explain to you. I'm going to take you through it so that it's not that bad. So you have two spectral triples with ones and with twos up there. And we have one of those, you know, horrible tunnels, well, big tunnels with a tunnel between A1 and A2, and one between the complex numbers with a module map in between, sandwiched with all sort of nice properties. And I want to make that covariant in some sense. I want to remember that actually D1 defines an action of R on H1, and D2 defines an action of R on H2. I want to keep track of that. So I need to throw in an additional number associated to all this data. So the data is these tunnels, which tell me essentially how to the idea is that, for instance, your Hilbert space H1 and Hilbert space H2 are quotient of some module, which I don't know what I call here, P in this slide. Okay, the quotient of some module. So this is how I kind of relate elements from one space to the other. They're completely unrelated to each other, but somehow they are quotient now of one common space where I can work and I can make sense of things. And what I do is I'm going to take a Hausdorff distance. This is this sup and inf here is a Hausdorff distance construct, the max of sup and inf of something. I'm going to take the Hausdorff distance between a piece of orbits. So you take a vector psi and you apply to it. Let's just follow the notation here. In my first blue box, you take psi, and psi is a vector whose d norm is less than 1. So it's like a state, quote unquote. And then you apply this group e to the it d1 again and again and again for a while. How long? Well, up to 1 epsilon over a ball centered at 0 of radius 1 over epsilon. And I want that to be close in the sense of this obvious metric, down there. I want that to be close to another vector in the other vectors in the other Hilbert space, which I moved along as well, but using e to the it2, except that t may have been a bit modified by one of those almost isometric isomorphism, right? It's not quite t, but it's something that I can measure how far from t it is in a very nice covariant way. That's it. That's the idea. You follow the orbit of a vector by you take a vector, you have its orbit, and you want that to be close in the Hausdorff distance sense to another orbit on the other side. That's really the philosophy, which I think is very natural. Now, okay, the math looks horrible because it's just the notations of Hausdorff distance. I take a sumph. So this means, you have to, the max is just to symmetrize. You can ignore it. Oops, I'm apologize. I clicked on. I use my mouse here. You symmetrize one in 1 and 2. Okay, so that's nothing. The sup is just a for all in this guy. So you say for all vector in Hilbert space, say H1, for instance, there exists a vector in H2 such that if you follow the orbit of H1 for a while, it looks almost like the orbit of if you follow the orbit of psi for a while, then it looks like the orbit of eta for a while. What does it mean? It looks like, it means that they're close in the sense of a metric, and that metric is written down there. And that metric is using, my big space P down up there, but I kind of rewrote it in a way that I hope is easier. It's actually defined on P, but when you apply it specifically to a vector from each of the vector spaces, it simply looks like this. It looks like you're taking the inner product of psi with some vector in P, and the same vector in P, you apply it to eta with the right maps. And you take the supreme over this again over your your states, which here are all the vectors whose graph norm, sorry, I shouldn't say graph norm. All the vectors with d norm less than 1 in P. So it's an analog of Monge-Kantorovich metric or cone metric. It's really an analog. And you just follow for that analog the orbits for as long as you can, as long as they stay close. And if you do that, the formula looks nice. If the formula with the square root of 2 is just the standard Gromov-Hausdorff thing in locally compact setup. Don't worry too much about it. You take the smallest epsilon for which you can find a tunnel for which all these numbers are less than epsilon. This gives you a metric again. And this gives you, in fact, a covariant version of the metric, which has all sort of nice property, but let me tell you what happens for spectral triples specifically. It said that if you apply this construction to spectral triple, then, which gives you a C-star correspondence and a group action, then they are 0 if and only if, the distance is 0 if and only if, you indeed have this conjugation by unitary of the spectral triple. So the whole package, right? The operators are conjugated, the Dirac operator are conjugated. The map that goes from A1 to A2 is simply the adjoint by this, so it's U, A, U star. So it's really, and it's a quantum isometry and everything is preserved. So this gives me an actual metric on spectral triples up to distance 0. So that's nice, but it's a lot of work, but it's actually, there is a progress, there is a process to it. There's a pattern that I repeat. And it's quite nicely behaved. But now, to conclude my talk, I should give you some proof that it's not a discrete distance, that we didn't work really, really hard. It does happen, by the way, in Gromov-Hausdorff world. There is a metric between differential structure that I don't remember who introduced it, I'm blanking right now, which was defined in a paper, I think in the 80s, or well, in the 90s, sorry, which was based on the Gromov-Hausdorff distance, but it was between differential structures. So you took the infimum of every possible metric, normalized, etc. And that was a discrete metric. This does happen, that after all this work, you get something trivial. So I need to convince you that, okay, this seems well behaved, but is it? And can you do anything with this? And yes, you can. So let me put a fractal. Okay, it's a simple fractal, but I figured for once I can put a picture. I'm going to take advantage of it. So, okay, first example of application. It's classical, so it's a nice break. You take the Serpinski gasket. So what it is this picture. And formally, one way to describe it is the attractor of iterated function systems with 3 affine functions written right here, where the V1, V2, and V3 are just the vertices of the big triangle in this picture. It doesn't matter what they are, of course, up to scaling, but this is what I'm going to use. So this is a nice object, okay? It's been studied a lot in the world of fractals.
But
Apparently,
you
it's
you
a
remove
prototype.
what's shown in white? You remove what's shown
Yes,
in white?
actually, yes, thank you. Yes, I removed the chunk in white, or in fact,
Yes.
better yet, I look at it as a limit of graphs, like this.
Oh, okay.
So there are different ways you can look at it as a limit. You're absolutely right. Just to avoid any, you end up with the same object, by the way. But just in my description, it will be helpful to look at it as a limit of just the triangles, literally. So you start with a triangle, apply these maps, you get 3 triangles, apply these maps again, you get etc. That makes sense? So I don't even remove or add, but you're right. It's the same object.
It's like the Cantor set. I mean, it's analogous.
Absolutely. Absolutely. Yes.
Okay.
Except that his dimension is more so.
It's like a 2-dimensional version of the Cantor set. So
exactly. And there is this.
It's a totally disconnected space. Compact.
Yeah,
Totally
it's compact, but it is connected actually. It's even path connected.
Oh, that's interesting.
Because you can.
Oh,
Yeah, exactly. That's the thing.
You're saying
Yes,
this
it's path
space is
connected.
path connected?
That's right. It is path connected. You can go from any point to any point following the. So that it's hard on the picture, but you take a point somewhere and you just follow the triangles in my graph because you never remove the lines. You see what I mean? So if you can go from the top to somewhere in the middle by just following the lines along each triangle. You never remove the actual triangle itself.
You remove the interiors of
but not the
white
lines.
triangles.
That's right.
Yes.
So you actually it's important, your path connect, actually.
Yeah.
So it's a geodesic space. Here's a natural geodesic metric attached to this, which is that you go from a point to another following the shortest path, where the length of each segment is measured the usual way, but the distance you get is completely different from the Euclidean distance. Well, it's equivalent, but it's not the same as the Euclidean distance. Okay, that's important for what I'm going to say, actually. So thank you. So this is a nice space, and it is a limit of stuff. So now it turns out. So yeah, this is my notation. So each of the graph, you don't need the mathematics here because we have very little time. Each of the graph in my bottom pictures here. Sorry, I generated that really quickly in JavaScript before the talk, so I hope it looks okay. But each of those pictures, I did not before this talk, before previous talk for the paper, but it was done kind of haphazardly. But you can look at this. Each of them I call SG0, SG1, SG2, SG3, and the actual gasket is SG infinity. Okay, whatever, just a notation so that we keep track of the finite graphs. So you don't need to have that. Then I'm going to define, so Lapidus actually in 2008 defined with his and so co-authors defined a spectral triple on this thing. And in fact, Michel Lapidus is doing a whole research program where he uses not geometry, but on fractals. Yes. Oh, sorry, Esther. And so the way he does it, I mean, I need to tell you just the general idea. Again, this would be more time than I have, but first, I remind you what I mean to put a spectral triple on a segment or just a line. So a line is kind of a manifold with boundary. I mean, I know it's kind of overkill, but there's 2 endpoints, right? So you have to be a bit careful. So what they do is they embed it into the circle. So basically, this is how I describe it real quick. It takes the C-star algebra of continuous function of circles by CP, but instead I look at them as function, on an interval with the same endpoint. It's a little easier notation-wise, with some value at the endpoint. And then you represent that on what I call L2 of CP. Lambda is just a GNS representation for the Haar measure, whatever. Normalize it any way you want, but I think they normalize it so that the length of this is 1. That, of course, won't matter too much. And then the Dirac, so that's your Hilbert space, that's your C-star algebra for one segment. And the derivation is just a usual derivation. There is this plus 1/2 thing, which is a trick they use to avoid the problem that in the construction I'm going to show you in the next slide, you would get a non-compact. If you didn't have the plus 1/2, then you would lose a compact resolvent property. So you shift your spectrum a little bit, so that 0 is not in it. That's it. That's other than that, it's just the usual derivative, takes the closure of that, etc. And then I just realized that, let me think for just a second here. I should not have put my, no, that's good, that's fine. I apologize, that's good, all good. I was concerned I gave you a skew adjoint version, but no, that's the right one. So then how do you put a spectral triple on C of 0, 1? You use this one, and you just plunge C of 0, 1 as an algebra into C of -1, 1 by this very simple map down there. To a function, you associate the odd version of that function f at the absolute value, composed with the absolute value. And then suddenly your algebra C of 0, 1 lies inside the continuous function of the circle, and we have a spectral triple there. You can check that, you know,
the even version. You said the odd.
Did I say odd? I apologize. Yes. Yes, I would fail calculus, but that's okay. Yes, it's an even function, of course. That's what I mean. You just symmetrize it, right? So that it's so you avoid the border entirely, essentially. That way you don't have to discuss what happens at the boundary. There is no boundary because you're really working on in the circle. In fact, by the way, I mean, there is, you could actually just use the spectral triple on the circle and just map it to each of the triangles. That would work just fine too. But there's a reason why this is done this way. It's useful because in the paper that I'm discussing right now with Michel, we actually apply this construction to a wider class of fractals, not just this one, but this one is easier to explain. So then it's kind of horrible to write, and I probably made a typo somewhere, and I apologize in advance, but it's very easy. To understand, what I do is I take this spectral triple on each segment, rescale it. That's what the 2 to the k in my blue box is about. You just rescale it, that has the right length. And and what you do is that you have a big, gigantic Hilbert space, which is a direct sum for each edge of the Hilbert space for the spectral triple on a segment. So you have, you know, that many edges. Now, the thing to keep track of is that at stage n on my graph, when I'm not finished yet on my graph with my triangles, I keep track of the whole history. Okay, so there is a spectral triple on each of the edge of the big triangle. Then there's a spectral triple on the edge of each of the smaller triangle inside, and going on at each. So you keep the whole thing. That's why there's a double direct sum. The first one is a stage. Maybe if I go back to the picture. So the n correspond to which of the graph at the bottom here I'm looking at, starting at 0, and the, what's the other index? So that's a k. So the k correspond to that. And then the j is inside one of those graphs, each triangle and each edge I'm talking about. There are 3 to the k edges. So you just keep going. So that's the idea. You just put a spectral triple of the segment on each of the segments. That's really just that. And then the way your continuous function on the Serpinski Gasket acts is by multiplication on each of those segments. You take a function on the whole thing, restrict it to one of the segments corresponding to the appropriate Hilbert space, and just it acts like this. So I don't know if it makes sense. I hope it does, but it's really just that. It's beautiful because the Hilbert space doesn't really care about the Serpinski Gasket. It's just a whole bunch of segments glued together with nothing. And the geometry of the Serpinski Gasket is captured thanks to the representation of the C of CSG infinity on that thing. So Lapidus was able to prove, for instance, that the geodesic distance is recovered by the cone distance. That was in 2008, right? So this also, you can recover some information, but the Hausdorff dimension is related to the summability of this thing and so on. So it works really well. You do get a differential geometry for the Serpinski Gasket using non-coherent geometry and these objects described, I understandably a bit fast, but I hope I gave you the intuition for it. So this is what I meant, okay? So it's a spectral triple, and it gives you the geodesic distance, not the distance so not what you're seeing here, but I can't draw it. Not what you're seeing here. What you're seeing here is like embedded in R2. In reality, the geodesic distance is a bit more complicated. I mean, there are lots of, for instance, let's see if I can explain that. Well, there are a lot of points that you can look at, you can do a calculation even after 2 stages. Some of the points are no longer at the same distance as the Euclidean distance. It's known the Euclidean distance is equivalent with a factor of 8, I think, to the geodesic distance on this thing, but it is not the same. And actually, we're going to work with the geodesic distance. It's important because this result that we just proved is that, well, if you look at this spectral triple I just told you at each graph level, and you use the one at the end, they do converge in the sense of the metric I described. So this spectral triple of Lapidus is a limit of very natural spectral triple on graphs in a very concrete way. This includes the not so hard to prove, but I believe new, remarkably enough, result that the geodesic distance, the Serpinski Gasket with its geodesic distance is the limit in the Gromov-Hausdorff distance of the graphs I've showed you in their geodesic distance. because it's not clear where to embed them anymore, right? I mean, the geodesic distance thing is all weird looking, right? It's not nice like that because it's a different distance. So that's the first example of application. It's all abelian, but it's still interesting, I think. At least I believe it's of some value. So now I'm out of time, am I not?
Well, how much more time do you need, Frederick?
I could probably get to at least give you an idea of what else I can do with that in 2 minutes.
Yeah, then
but it's not good to go over time.
Yes.
Okay, so I'll start from the end and backtrack. That's weird, but so I have another result. So actually, this result, which is just now, is valid in the when the limit is non-commutative too. There are non-commutative limits in the paper. It's just it's kind of a lot longer to write. So I prefer to just show you. So I can also approximate Dirac operators, spectral triples, sorry, on say the continuous function on the 2 torus or the D torus, or for that matter on even quantum tori, using matrix algebras and Dirac operators there. So what are the Dirac operators that are involved in this? So there's a nice result for this metric where certain Dirac operators on tori are approximated by matrix algebras. So what are the matrix algebras? What are the Dirac operators? Normally I have a spiel to try to explain to you why those are natural, but I'll go straight to the answer. So for this very simple theorem, for instance, well, the proof is horrible, but the very simple to state, for this special case of the result in the paper, Cn and Sn are the clock and the shift matrix, which are very commonly used in, and say, look at Weil quantum mechanics on finite stuff in his book, or Tuft, I probably mispronounce that horribly, but I have no idea how to pronounce it. Work on trying to find a model for quantum mechanics, or in papers of, I believe they did show up in Dr. Cohn, Douglas Schwartz paper on that I mentioned in '98 on compactification using quantum tori and string theory, etc. These are natural objects, and there is actually some amount of literature. John Barrett worked on that, etc. On approximating, say C of T2 in particular by these algebras. This makes perfect sense metrically, and I've known that for a while. But what's interesting is that you can put a Dirac operator on this, and here it is. It's this blue box. So it's a bunch of commutators, and if you ask commutators with what, the Hilbert space H is it's a regular representation. The Hilbert space H here is the space of n-bind matrices. So it's not the matrices acting on Cn, it's a matrices acting on themselves. That's a right Hilbert space for that. And then my gamma matrices, okay, as usual. And these are scaled version of commutators with the self-adjoint part and the the real part and the imaginary part of Cn and Sn. The reason why I have imaginary and really is just to keep my Dn self-adjoint. It's just a technicality. The important idea is I just take the commutator with Cn and Sn, where Cn is kind of your position variable, your observable, Sn is kind of your momentum variable, and they are related by the discrete Fourier transform. So really they kind of act on derivation on each other in a natural way. So it's a natural object. And this has happened, and this has appeared in the mathematical physics literature. And the limit, I don't tell you why, I just show you, but the limit looks like this. It's a Dirac operator on the torus, where D1 and D2 as it's a canonical moving frame on the 2 torus, but then you have to multiply them by the real part, and the imaginary part of the coordinate u and v. U and v are my coordinates here. In physics, maybe you would say, that u and v has the angle phi and theta of your torus, and then it would be the cosine and the sine of phi and theta in front. So it's a strange Dirac operator, but it is a limit of this finite. So in the physics literature, you will find statements to the effect that Dirac operators on the fuzzy tori, the C star of Sn, converge in some sense to something on the torus, but that statement is not formalized in any way. And here is actually a result that takes those objects that are of interest in mathematical physics and does indeed prove, in the sense I have explained, that they do converge, making the metric non-discrete, right? I mean, it's an interesting one. And as I said, just as I not explain more than that is my conclusion, this result is valid with 2 replaced by D, with more complicated algebras for there, and even for quantum torus, although the Dirac operators looks a little more complicated, but you can even do that for non-commutative limits. So I have a result of non-commutative limits as well. And that's it. So that will be my conclusion. Sorry for the going over.
Very much indeed for your very fascinating talk. Let me have my clapping hands. Yes, good.
Thank you.
Let me also, I'm trying to switch video on. Yes, okay. So really, thank you very much, Frederick. And now we can begin firing questions at you. So anybody who feels like, please fire the will. Any questions to Frédéric? Please go ahead. Konrad, you have your hand raised. Go ahead.
Yes. So I think you might have mentioned it, but then stopped saying it. But the dual propinquity is complete. So you said that. But are there any conditions or any reason why you'd want any completeness for the spectral propinquity? Or?
Yeah, so the spectral one at the moment, so that's a good question. And no, we did not rehearse to everybody else.
You don't have a deal with your student. Okay, excellent.
No, yes, I don't. I was like, okay, maybe something happened but I wasn't involved. I'll ask Piotr. Yes, so that's a very good question. Okay, what about the completeness of the spectral? It's a hugely interesting question to me, because imagine you're doing your physical model or you're doing fractals, say, and you know exactly what you want to do at the finite stage because it's not too bad, but you would like to have actually a spectral triple on the limit, and that may not be less clear. So completeness would say, well, just don't worry, prove it's Cauchy, and then you'll get something. So I am interested in that, and there are partial results. This theory I've presented is congobulated by putting together various ideas I've developed over the years. So certainly, as you mentioned, the metric piece is complete. So if I have if I have a Cauchy sequence of spectral triples, I do have a limiting quantum metric spaces. Step one may not come from a spectral triple, but there is a limiting quantum metric spaces that comes from the completeness of the metric. Second of all, there's more. There is actually going to be an action of R on the module by unitary. We're still going to have that. Whether the generator has a compact resolvent, that is not something I have worked out yet. If I had to guess, the answer is no, not in general, but under some conditions, yes, we're going to be able to ensure that the limit generator will be, in fact, as compact resolvent. That's the part that's missing. You will have, so if you have a Cauchy sequence of spectral triple, you will end up with something at the end that looks like a spectral triple, except you don't know if the resolvent is compact anymore. It might be. I mean, the reason why I'm hopeful that the condition might not be too hard, though, is because you will know the graph norm will have compact ball. So you're close to it. You're close. That you know just by using the completeness of the modular thing, the covariant thing, and all that. So the paper is not written, but if you plug together results from 3 or 4 different papers, you get that close to it. So it's almost complete, but I need to check the compact resolvent. I might get a slightly weaker condition, which is okay, which just means we need to add things, which wouldn't be totally surprising because that's what happens in differential geometry. You need some curvature conditions to avoid in the Gromov-Hausdorff convergence to make sure the limit is still a manifold, otherwise things can degenerate. There might be something having to do with, the spectrum should not kind of become continuous at the limit or something bad like that to avoid that. But so modulo this, we already know a lot about completeness, but we don't have completeness exactly of that metric, but we have a lot of completeness result on the building blocks that give us something, a candidate for the limits. So already have a candidate. We just don't know if it's a spectral tripology.
Okay, great. Thank you.
That's a good question, actually.
Now, Andrzej, your turn.
Okay, thank you, Piotr. Hi, Frédéric. I have 2 questions now. So one will be about something that's on screen right now. So if you have this Dirac operator for the torus, it looks like, this is not really the typical one, but I mean, can you calculate? I mean, can you say something about what metric it gives? I mean, probably it will be some metric with a local scalar curvature that's non-vanishing. So
yes, thank you. So that's also a good question. Thank you very much. Since I was rushing at the end, I wanted to mention that. So Dabrowski and Andrzej have a bunch of objects like that. They call the curved quantum tori. And this is an example of it because your RU and your IU commute, right? So it falls inside this sort of, so yes, it is a deformed version of the flat one. It does have some non-trivial curvature. I confess that this is like, by new, I mean, this paper is 3 weeks old, and during those 3 weeks I've been teaching. So this is essentially, as I'm afraid, my knowledge of it at the moment, but I like the results I wanted to get. So I don't know the exact curvature. There are, so this is a very good, but this is a good question. Yes, it is a non-trivial, non-flat but interesting operator. And it is of the same family as yours. I do not know what the curvature is at the moment, but this should be calculable. What is interesting is if you square that thing, okay, so there is this phenomenon of doubling of the fermion, right? That's what a physicist would say. I have four gamma matrices instead of 2. That seems to be a recurrent theme in these sort of finite dimensional approximation of Dirac operators. And so that is the first mystery, which I'm sure, is interesting. I mean, of course, when you Dirac operator, anyway, I'm sure there are many ways we could discuss this, but I think to me, personally, it's still a tiny bit of a mystery. And the other thing too is, if you square this, then it becomes, nice. It's just the usual symbol of the Laplacian, except you have too many variables. You have 4 instead of 2, but so the symbol of the square of this is kind of what you want it to be. So it's well behaved that way metrically. But the Dirac operator is a little weird. Now there is another one recently due to Barrett and Gaunt, another candidates, if you want, for the finite dimensional bits, which gives you another limit. So they have more terms. They have but the more terms involve gamma 2, gamma 3, product of the gamma matrices, which involve anti-commutators. And by doing that, they get something they claim as a better curvature, better behaved, and especially relative to the curvature tensor than this one. They had a reason why they thought this one was a little weirdly behaved. To me, I mean, I'm happy that I think there's also work, by the way, but I haven't written it down because I just finished this, but I'm pretty sure it fits. It's same sort of mechanics, just more notations. So yes, I don't know what the metric tensor is, but I'm sure it's computable, and it's going to be one of your twisted ones, actually. So it's an example of that. And I should say, when the limit is non-commutative, I still get essentially one of your, it's not clear which one because my presentation looked quite different, but it is a Dirac operator that obtain by deforming the flat one using things that commute with your algebra. So it's exactly your idea with Ludwig. Yeah.
And a second question that I was trying to ask for earlier, I mean, when you have a spectral triple, which you call a metric spectral triple, so with a Dirac operator that satisfies this condition, that the commutative Lipschitz, does it hold when you perturb the Dirac operator by something bounded?
Yes, if you don't perturb it too much.
What does it mean too much?
The norm of the perturbation should be reasonably small, I believe.
Okay.
Smaller than what is it? Smaller than the radius of the space, or something like twice the radius of. Because if you and the reason is not difficult. It's just if you perturbate it too much, suddenly you might introduce a kernel. Right, the d plus m comma a could be 0 for more a's. But if actually m has a small enough norm, you can avoid that problem. And then and in fact, it's continuous for this metric I've written.
Okay.
So the perturbation, it's bounded. You just add a bounded perturbation. Then, in the sense of the metric I just described, you have a continuous family. Yeah. Yes.
Okay. Thank you very much, Fred.
Anybody else?
Yeah.
I don't see any hands.
Yeah, I might have one
Go ahead.
One small reminiscence. When you were talking about C plus C and the double and so on, it reminded me of something, but I'm not even sure that I wrote it somewhere, which for me was indeed a very good example of the Gromov distance, which is that when you take the double space-time, Euclidean. And so essentially, I mean, to simplify, let's take just the product by a 2-point space. Now, what happens is the following. What happens is that somehow when you compute from the natural spectral triple coming from physics, when you compute the distance between the 2 points which are above the same point, classical, if you want, this distance is extremely small. I mean, because it's like the inverse of the Higgs mass or something like that. And I mean, so I remember that but I don't know if I wrote it down, that I consider this as a very good example of the Gromov distance, because imagine that for the spectral triple, you don't take the simple thing, which is just the product metric of the Euclidean, of the Riemannian metric by what happens in the finite space. Imagine that you leave yourself the freedom of taking a different metric on each of the sides. Somehow, if you want, it's like a sheet of paper which has two sides.
Got you.
And they're
Sure.
very, very close to each other. So imagine now that I take two metrics which a priori are quite different on the two sides. But what you know from the Gromov distance is that in fact they are very close in the Gromov distance because precisely there is a space, which is the total space, which exactly satisfies the fact that the Hausdorff distance between the two is very small because it's given by the inverse of the Higgs mass. You see? So I
I do, and in fact, yeah, no, that's super interesting. In fact, now I have to ask a silly question. What happens if you take that constant to infinity, the Higgs max, so that the two sheets become almost the same?
Well, okay, indeed.
What do we expect the limit to be?
Yes. Okay.
Yeah.
So
now I can make sense of it. Yeah.
Right. So I think it's very interesting indeed to investigate in that generality what is going on. So
okay. Yeah, thank you. And actually, I wanted to point out, and again, something I forgot during the talk, which is an aside, but I believe that you worked with Walter, right? Who is in the, was on the call at some point, sure. on something that has some flavor to what I'm talking about.
I'm here. That's right.
Yeah, Walter is a
yes, no, it's okay. The last thing I want is to trap someone who decided to take a little break. This is something you think about when you teach a class. You know that if you call on students, sometimes you have a blank and you can't guess why. So
that's the only thing. Sorry.
Yeah, but there is a work by Alain and Walter about truncating spectral triples, which I believe is in the same philosophy. It's a different method, okay? But I just wanted to point it out as a related work that there is this interest in that case. What happens is that their truncation is our spectral triples on, is it operator systems? Yes, that's what I thought. And there is definitely a way so operator systems, immediately I'm going to think the Kerr distance. So there's been some work on using operator system in Gromov-Hausdorff long ago. And so this could be relevant to that story. I'm a little bit obsessed with these algebras because I like the idea that they are non-commutative spaces. Like it's easier for me to understand. So this is why I went through it's more technical, as you can plainly see, but this is the reason why I want to pay this price. And whether I'm right or wrong, that's history will tell, as we say. But I wanted to point out this other work because so the way I would describe all of the ideas I talk about is that this idea of finite-dimensional approximations, they're like a dense sense in mathematical physics, but of measure zero, right? I mean, like a lot of people talk about it, but it's not like everybody talk about it all the time. It's just that you encounter this concept often. So whether or not my metric is the right way to do it, that's that's for me to establish in time. But I think there are interesting problems. We just discussed one with Alain right now, which I think is super interesting because that's where I want to go. But
well, I think actually in what you say, I mean, it's very important to understand that there are, if you want, abstractions which have been very well understood by physicists to approximate space or space-time by finite sets, ordinary sets. And abstractions come from the inflation period and the fact that, so I mean, these abstractions are very well there. However, these abstractions do not exist in the non-commutative world. So for that reason, it is extremely important to have extended the Gromov distance, the convergence, and so on to the non-commutative world, because it is shown, if you want, in physics that the naive idea of approximating space-time and so on by finite sets or by discrete sets and so on doesn't work. It doesn't work for very strong reasons. But this is not at all the case in the non-commutative framework. I mean, so for that reason, I think it is essential to do the groundwork that you are doing. I think it's and that Mark, of course, did from the start. But I think this is quite quite important. Yes, definitely.
Well, thank you very much. So that concludes my talk pretty nicely. But
very nicely, Ludwig wants to speak.
But
yes, I wanted to ask a question, a little bit deeper into the question of Alan, a comment of Alan, and so if you have just one in the same space, or manifold, let's say, two different Riemannian metrics on it, Gromov distance between such spaces 0.
No.
No. So, the grammar files of distance remembers a metric. So meaning that if you have two different metrics, you will have to do, the distance will be strictly positive, for sure. What happens is there is a result due to Chigger, I believe, and Gromov, and that school of thought, where if two, so there are conditions, and if two manifolds are, we good?
Go ahead.
So if you have two manifolds and they're close in the grammar files of distance, and the actual manifold, and there might be a curvature condition that I forget on top of my head, then the manifold must be homeomorphic. So but this doesn't, obviously you can always approximate a manifold by finite points, right? So they have to already have some structure. But so what happens is when you're close enough, manifolds that are close enough must be the same manifold, but the distance does remember the metric itself. It's not a differential distance, a distance on metric. There was work, there's in fact, here and there in the literature, there is work on trying to make sense of convergence of differential structure, not just metric. And this is, I believe, I mean, again, there's a lot of literature, right? But I do claim that this work I've just done is new, even in the classical picture, because their notion of convergence of differential structures there doesn't work. So either it's kind of ad hoc, which we can, you know, there are a lot of ideas, convergence of, there's something based on currents that kind of is nice and ad hoc, and I should prove, you know, that it's implied by my convergence, but it's ad hoc, or it just doesn't work. What people try to do is they took two manifolds, and X and Y, and then they took the infimum of the grammar files of distance for every metric, probably normalized to 1 or something, so that it doesn't degenerate. And they prove that this is discrete, which is a corollary of that theorem I mentioned. So there is nothing really on differential structure between Riemannian manifold. There is something on Riemannian, but including the metric. Does that answer the question?
But this is very parallel to what Alain was saying, right? That,
yes. It is. So there are certainly rigidities in the classical picture, which we certainly don't have in the, I mean, because spectral triples allow you to do a lot of things that, you know, obviously manifolds don't. So I mean, there's lots of work, even in the classical world, with this stuff. I mean, you take a bunch of manifolds and you look at the sort of conditions that you have, so they converge to something that may not be a manifold, but it's not completely degenerate, an Alexandrov space, they're called. Well, what's this Dirac's operator there? I mean, it should be a limit of Dirac operators on a manifold, right? So there's all these questions that I haven't touched. This is just fresh out of the oven, but which are on my to-do list for forever. You know, what I do is what I feel inspired by at the moment. But this even a classical picture, the modules, by the way, even the modules. So there were some convergence on modules, but they're very rare, and they're not the same. They converge to vector bundles. So they take the vector bundle and they just look at the total space, and then, you know, they put. So what they say is, you know, you have a manifold, you have a vector bundle over that. And if your manifold has a metric, they find canonical ways to associate metrics on the, what they would call canonical ways to associate metrics on the bundles, and not canonical with quote, but so natural ways to do that. And then they talk about convergence of the total space in the sense of locally compact, this time, but nothing about the module. This is not the same, right? Because the total space is not, you lost the bundle structure, it's just it's a total space. So the module structure, that's new. Even classical picture, there is no. So I think by taking a functional analytic standpoint, sort of looking at it from as a functional analyst, you get all these ideas, because you don't think in terms of bundles versus, you say, oh, they have a modules and have norms on it and they have the right properties. So it opens that too. So even the classical pictures, there's work to be done. But I'm very much a non-creative guy. I must say that by training, I'm more of a functional analyst than anything. So I tend to focus on the non-creative story. That's what really fascinates me. But I do think there is work to do. I mean, in the classical picture there with these new tools as well. But I departed a bit, but I wanted to point that out because I think it's not trivial.
Yeah, that's quite interesting.
So yeah, sorry, Ludwig, maybe. Thank you. I mean, okay. I think that there's something.
Anybody else? Any further questions or comments? Yeah, go ahead.
So I have 3 questions. So the first question is in the context of dual propinquity, inducing topology, Gromov-Hausdorff topology.
Yep.
Is it known how equivalent should be L semi-norms to induce the same topology?
Let's start that again. I'm not sure I totally got it. So you want a condition on the L semi-norms?
Yes.
So you want the L semi-norm to be a Lipschitz semi-norm? You basically want a full duality result. Is that what you're asking me? Maybe I didn't understand it the right way. You would like to know what condition I put on L so that L is actually a Lipschitz seminorm?
No.
Nope. Okay.
How equivalent should be L seminorms to define by this dual propinquity the same Gromov-Hausdorff topology?
To get actually the same distance, you mean, like so that I get the same distance instead of something.
No, topology.
Well, the topologies, they are equivalent. So okay.
Independently of the choice of L? No, it's strange.
What do you mean by L? Maybe I don't understand. L for me means the L seminorm.
Yes.
We go back to my notation.
Seminorm. Okay.
Yeah, so it only makes sense if L comes as a Lipschitz seminorm of a metric space, right? I mean, otherwise I don't. So you have a map. Let me first explain what the theorem means, maybe more clearly, so that we have the same notations. So you have your X, M compact metric space, just a good old compact metric. To that you can associate obviously C of X, L, where L is a Lipschitz seminorm for that M.
Yes.
Okay. That map becomes an homeomorphism.
Yes.
Just like that. That makes sense? So if you have a bunch of metric spaces converging to the Gromov-Hausdorff distance, then C of X and the associated seminorm that come from that metric converge for that metric and vice versa.
Okay.
Okay. Now, the problem, the hidden problem, maybe that's why I was asking, is if you give me an abelian system algebra and I put L seminorm in the sense of this definition on it, that L seminorm may not be a Lipschitz seminorm. And so then I mean, it's not in the range of that map, right? It makes sense to talk about that convergence, but they have nothing. They're no longer coming from a metric on the space. They're more complicated. And there are examples of those. So that's where L, of course. But yeah, as long as your L is an actual Lipschitz seminorm, then yeah, you're in the range of that map, and so this is equivalent topology. Yes.
Okay. So all are equivalent.
Yeah. Yeah.
Okay.
That's right.
Thank you.
That's right.
The second question is in the context of this classical distance between vector bundles.
Yeah.
So for this at least Gromov distance, you have these two versions, non-commutative and this classical one.
Sort of, yeah.
What is this classical counterpart for?
There is no real classical counterpart. What there is, not really. No, that's the thing.
Okay.
So what there are partial results. I'm aware of essentially one general strategy. The general strategy, and it's not very common, but the general strategy is you look at the total space of your vector bundle. So you forget the vector bundle. Just look at the total space. And then you just look at it as a metric space. And what happens is in differential geometry, there are natural metrics you can put on the bundle. So like you have your metric on your manifold, you choose a connection on your bundle, and poof, you get a natural metric on the bundle. And they talk about the convergence of those sometimes. It's not very common to begin with as total spaces, but it doesn't remember, sorry, the vector bundle structure. You don't even know if the limit would be a vector bundle on anything. It's something, I mean, on top of my head, I mean, it probably does work just because of my habit of working Gromov-Hausdorff. You can cook up something, but I would say in general, that's not clear. Whereas with modules, you remember the vector, the fibering, if you want. You do remember it's a vector. It's not just, so you have convergence of both the base and the module, and the limit is again a fiber, the action is preserved. So the module action is preserved. Therefore, you do preserve the fibers, not just, that makes sense. You really look at it as a bunch of fibers converging, not just as a total space where you forget the fibering. And that is just non-existent, literally. I think it's non-existent because it's not natural. My definition works because after some examples, I was able to say, oh, look, it does work on free modules, on manifolds, I have lots of examples, but there was a little bit of a leap of faith, which is very natural in functional analysis, not so much in geometry, where I lift sections. And I mean, so if you have a vector bundle, okay, let me explain that another way. How does that work for a vector bundle rather than a spectral triple? For a vector bundle, what you would do is you would take a connection on your vector bundle, which is a Hermitian connection, a metric connection, okay, on your vector bundle. So you have a metric at the bottom on the manifold, then you have a vector bundle over this, and it's you put a metric over that vector bundle. And you look at it as a Hilbert module with extra information coming from a connection. Now, that connection, with a little bit of work, but not too much, but you can make a norm out of it. And it's really just an operator norm. What operator norm? You look at the connection as applied to a section. So that thing as an operator that goes from the tangent or cotangent space, but let's say the tangent space to the bundle, where to each tangent vector field you associate, the connection along that vector field of that section, right? That gives you something in the Hilbert module, so you can take its norm. That's a D norm. That it turns out it satisfies the properties I've described. So you have convergence of the bundle and of the metric part of the connection, not the entire connection, but the metric piece of it. That is not done. I mean, I think for when you do non-con geometry, if you look at differential geometry, sorry, you don't find a ton of people taking norms of connections. It's just not a thing. I mean, I don't know, it just, for them, a connection has it has, of course, a deep meaning. It's one of the most important objects in differential geometry. And this important object, they manipulate them as derivations. It's a way to take derivatives, quote unquote, of things. Not so much as a Lipschitz seminal. That I would say that in hindsight, it might sound trivial, but apparently that wasn't noted. And when you do that, suddenly you can use that tool to say, well, I can make convergence of modules just fine. And that's completely new, even in the classical picture. I mean, on which I've done nothing, but it is new. Yeah.
Sorry, I thought that my questions are simple. So the last one is really simple. For the Serpinski gasket,
yes.
How different is this spectral L from the classical Lipschitz semi-norm?
So there's a factor of 8.
Sorry?
There's a factor of 8. It's equivalent.
Factor. Okay, very simple.
It's equivalent. Yeah. So it's the Euclidean distance is of course shorter because you don't have to take a detour. So that's the bottom, and so the usual distance is less circle than the distance on the Serpinski gasket geodesic, less circle than 8 times the Euclidean one. So you Lipschitz seminal, you flip it really. Yeah, it's the other way. 1 over 8, I guess. But it's
but you are talking about this Lipschitz for this geodesic.
Yeah. So it is a Lipschitz distance. Given a good point. So it is a Lipschitz distance. So the spectral triple constructed by Lapidus and co-authors gives you the geodesic distance. That's right.
8 times bigger than.
But between 1 and 8, depending on what. Yes, because it's equivalent. So yes. So it's interesting. I asked Michel about that. 2 things. Saying, 1, I have no idea where to embed the Serpinski gasket that it looks like it should for the geodesic distance. I don't know if it's doable. I just don't know. I'm sure it's doable, but I don't know if there is like a nice space. And maybe it's an easy question, but apparently nobody knows. So when we draw this thing, this is in R2. And so the metric between points is wrong. And then, you have to follow path. It's not the embedded metric. And the second thing is, this is the first time ever this result here does imply in particular the convergence in the Gromov-Hausdorff distance of this graph to the Serpinski gasket for the geodesic distance. It's obvious they converge in the Hausdorff distance in the plane. You look at the picture, okay, they converge. The distance between, it's 1 over 2 to the n between each graph, the graph at stage n and the limit, that you can do by hand. But the Gromov-Hausdorff distance is not much harder. First of all, the Hausdorff constant implies, so the Gromov-Hausdorff distance, convergence is not much harder for the geodesic distance, but it is new, apparently, just so you know. It's not like the crux of the proof, but I was interested in that. Nobody looked at it this way. Like they talk about the geodesic distance all the time, but there's nowhere does they mention that technically speaking, it's not the same to converge with the usual, the R2 distance versus the geodesic distance. They're different. And with the geodesic one, you don't, this is where Gromov again becomes useful, because Gromov distance, I should not say Gromov because that's like terrible terminology. Sorry, I'm tired. The Gromov-Hausdorff distance becomes useful because suddenly you don't have a natural embedding anymore. The R2 is the geodesic Serpinski gasket does not embed isometrically in R2. Let me put it this way. It embeds isometrically to other things itself, whatever. And also, by the way, the geodesic distance on each of those little graphs is not the restriction of the geodesic distance at the limit. Okay? It's more complicated. So actually, it's a key observation to the proof. It's not a very difficult proof, but I like it because it's easy for a change. So because the quantum torus proofs are much more involved. But this one, you just restrict to the vertices. So the vertices at each stage embed isometrically into the limit, but not the whole triangle. It keeps being deformed as you go along. So this, you really do need Gromov-Hausdorff if you talk about geodesic distance. It's no way, it's not hard, but it's not trivial, if you see what I mean. So those are 2 points I think are kind of fun about this geometry. Yeah.
Thank you very much. Yeah.
Very well. And I knew you were going to ask me questions. I was waiting. I think you always ask a question. I believe this is
yeah, it's traditional. Yes,
which is nice.
I could have more questions, but
it's good. It's good. I mean, it's nice to know that you're not going to be dry at the end of this talk. It's a given. So that's good.
So what about one more?
Yeah, sure.
I know one.
I mean,
okay.
Piotr is the master of ceremony. Yeah.
Okay, Piotr.
Yeah, go ahead.
Okay, so the question is about these Jordan-Lee algebras.
Yes.
It seems that this Lipschitz semi-norm depends only on this Jordan-Lee structure.
Yeah. So yes, the short is the technical.
Do people consider this Lipschitz semi-norm on Jordan-Lee algebras which do not come from sister algebras?
So by do people consider, you mean me and Mark and Conrad? And the answer is no. I believe we haven't. You could. I think it would be zero problem. The theory would carry complete. They have to be complete. Okay. So you would have a complete Jordan-Lee algebra with inside of it a dense sub-Lie algebra with all everything I've written here. Unitol, so you have to have a unit of some sort. And I'm trying to think really hard, but I mean, because I believe that that's all you need. Like you will be able to make sense of states and so on. Yeah, it will. The theory will carry. I can do it in my head right now. It will carry because it's the same proof. There will be no. So you can extend this metric to Jordan-Lee algebras.
Okay.
And it will be complete and
the opposite.
So on.
What about the opposite direction? Can you avoid Jordan-Lee algebras?
So that's a good question again. So you could, one thing you would want to do because of the talk I gave is to have L defined on a dense star subalgebra. I think that's one example of, forget this Jordan-Lee thing, just work on the whole. Of course, it does come often like that. I mean, to be honest, the Jordan-Lee subalgebra thing is a technicality. I mean, most semi-norms, I think also, I mean, if I don't know of any not made up example of a semi-norm that we use on the neutral system algebras of the type I'm discussing here, which is not defined on a dense subalgebra of the whole thing. The problem is the distance zero problem. So where things go bad is there. I passed it. At the bottom here, you see how I preserve like if you have distance zero, you have a star isomorphism that actually map one semi-norm to the other. That happens on the self-adjoint part. It's not clear that this would happen if your semi-norm is defined everywhere. And the reason is because of the role the states play, right? I mean, your distance is different on the state space. So maybe one way to go around that would be to not work with state spaces, but to work with like the unit ball or something like, or something like removes the Hermitian property. But I don't think that. I mean, this picture I think is the price you pay by this restriction is well worth it for other reasons. But yes, so because we focus on the distance on the state space, you end up with the only part of the metric really only matters on the self-adjoint element. It doesn't really, I mean, look at the Morse converged metric. Look at this definition. I mean, where is it? Here, you could replace, actually I did write it with A in the self-adjoint part. I could have written A in A instead of A in self-adjoint of A, but you get the same exact object because you decompose A as real plus I times imaginary, and the phi of I times imaginary is 0. So because phi is Hermitian. So this is kind of like what you get, right? I mean, this is the metric on the self-adjoint P, the self-adjoint net. So the Jordan-Lee algebra only arises because since the information is contained on the self-adjoint part, well, I need to put a multiplicative structure on it, otherwise I lose the multiplicative structure. That's basically what happens with the metric if you approach it as Mark did, and then in that case, you lose the multiplicative structure, so it's not good. Well, for me, I like the multiplicative structure. So if I want to keep it, what's left of it is the Jordan-Lee structure. That's why. By the way, since Conrad, I see Conrad at the bottom of my screen there, being bored all the way. No, I'm kidding. And so We in our paper on the Bunz-Dedens algebra. Don't ask me why it's in that paper. There is a reason, but the paper on the archive where we apply some of that stuff to just the metric side. There is a proof that actually if you remove the multiplicative structure, so you take exactly everything I talked to you about today, but you drop Jordan-Lee algebra, just subspaces, no algebra, and you drop 0.5 because it makes no sense anymore. You recover essentially Mark's distance, essentially, on C-star algebras, but you could even drop that, so that's the detail. So basically, this Jordan-Lee algebra plus this 0.5 is exactly what makes it a metric for C-star algebras versus just for other unit spaces. So if you drop Jordan algebra too much, then that's what happens. You just drop the multiplication structure entirely. So distance zero would just be a distance zero between spaces with orders, which is still nice, but it's not the same. So why is it important for me to have a multiplicative structure? How do I talk about modules? I mean, it's hard, right? That's a module of another unit space or no person. It's not undoable. I can probably cook up a definition, but whether it's useful or not, I don't know. What's a group? I mean, group actions, of course, well, they're well defined, but group action by star automorphisms are different beasts than group actions by positive linear maps, right? Invertible maps. So if you want to preserve, to be able to discuss convergence of group actions, convergence of modules, then it becomes kind of useful to have C-star algebras. And then Mark, if you wanted, could have probably told us something about why he in his work he also found, but I think it was for modules. Yes, I remember now. In his work for modules, I mean, he did the Leibniz relation. I mean, at some point, this multiplicative structure stopped playing a role. So that's why we need some multiplicative structure. It just turns out that the multiplicative structure on the self-adjoint part of a C-star algebra is a Jordan-Lee algebra structure. I'm pretty sure I need Jordan-Lee algebra. Well, no, there are some exceptional things. I don't know about that, but most of them will be of that form anyway. There will be sub-algebra of the self-adjoint part of the system.
Yeah, many of them.
Yeah. I mean, with some exception, there's some exceptional Jordan algebras, but which we could definitely do this theory with Jordan algebras, with Jordan-Lee algebras. It just hasn't been I haven't had a motivation to do so, but it could be, yeah, we could work.
Okay, so maybe one more. In the case of topological or metric monoids, there was a condition, yes. Delta K of delta J of G and so on, so on.
Yes, this thing, yeah.
So if epsilon is 0, I would like to understand what's the meaning of this. If they are,
it's an isometry. It's an isometric isomorphism, literally.
Is it obvious?
You can prove that it's an. It's not obvious, but you can do it. It takes a little triangular inequality work.
Are not invertible. How this implies?
No, but they become. They become because it implies they're invertible.
For groups, I do agree. I agree for groups. But for monoids, I don't. Yes. I cannot see that this implies.
It works too. No, it was because they're unital. So you can always. Let's see. You can drop G prime. You put E in there, so it becomes the identity. And then for H, let's see what you take the other sigma, and you're gonna get the distances less than epsilon between. So you can use triangular inequality. I mean.
Yes, I see.
To get the distance from G to sigma 1, let's see, sigma J, sigma K, whatever, of G is less than epsilon, or 2 epsilon or 3 epsilon.
So
or whatever.
Using triangle inequality first, you have to prove that zetas are isometries.
Yes. So instead of equals 0, they would literally be isometries and the group morphisms, and that's the proof that this is an isometric is a lot quicker than the propinquity version, because I mean you just literally do that. For every epsilon there is this thing like that, and it's just a limiting process because of you notice how I assume my monoids are proper. So all the unit balls, all the balls are compact, the closed balls are compact. So you get you get a bunch of equal continuous maps, and they have a limit. I mean it just works like that. But yeah, the case epsilon equals 0, you just obviously epsilon 0 is horrible in my 1 over epsilon ball. So by convention, we would mean that it becomes an isometry on the entire space. That's what it means. And then what the epsilon does is that instead of looking at an isometric isomorphism over the entire space, you look at something that kind of behaves like one, but not quite. but on a large chunk of the space. I mean, I don't have a slide about this. I should have probably, but if you look at the paper where this is, I do prove that this little blue box gives you like 5, 6 is equivalent to 5, 6 conditions, which include things like delta of sigma j of g, sigma j of g prime, comma, sigma j of gg prime, is less than epsilon, some, 3 epsilon or whatever, there's a constant. So if you see what I mean, like there is a way to, so it's saying that it's almost multiplicative and it's almost invertible and it's almost isometric and all that. And this can be quantified very nicely, but this blue box, the advantage when you put it this way is that it gives you a nice metric. If you do it with like, like listing what you want, because the epsilon is not, you don't get a metric, the triangular equal doesn't work. So this is kind of a nice way to get a nice metric. It's just a trick. And I like it because it looks like taking an adjoint kind of thing. Like they kind of adjoint in some metric sense. It doesn't make any sense, but it's kind of pretty that way. So it's, but everything you're thinking about right now, Thomas, like, is it almost multiplicative? Does it map the inverse almost? It all works with a triangle inequality.
So is there a similar result for compact quantum groups?
Not that I know of, but this is something big. And the reason why the answer is no is not big. I think it's quite doable. The problem is I don't have a good example of a quantum compact metric quantum group. I believe that Jens, yes. There are some, by the way. I'm not saying there's none, but I guess I was waiting because I know that some people, some of them in attendance, were looking at SUQ2, for instance. So it would be nice if SUQ2 was fitting that framework with its usual Dirac operator. We don't know that yet. We do know the Polish spheres now, so that's very, very nice. Thanks to Konrad and Jens and Konrad. Who was the other person on the last paper for the?
And Konrad is no longer with us.
Oh, sorry, you had to go. But anyway, so there is some result, but not yet SUQ2. There are some quantum groups that are known to fit that framework. I don't remember what they are on top of my head, but they're not the one you guys usually talk about. So I was waiting for more classical example. But the answer to your question is, because of what I know about the construction behind the mechanics of this, yes, I fully believe that we can make a covariant metric with quantum groups and coactions. But there are certain difficulties involved because it's hard to put an L seminorm on a tensor product. So this is, but with spectral triple, that we have a better idea what we want. Just with seminorms, a bit trickier. But I believe that, yes, the framework could be generalized. I'm optimistic about that. But I'm waiting for, I tend to kind of not go beyond having some juicy examples. And my juicy examples tend to be quantum tori related marks, tend to be the spheres and the coadjoint orbit of Lie groups. Those are, we splits the research a bit that way lately. And Jens, Konrad, etc., had a project to look at quantum groups, SUQ2, etc. So we kind of like avoid conflict by working on different chapters like that. So until SUQ2 is out, I don't want to look at it. There's so much to do. But yes, I believe very much that you could get some result there too, once we have enough examples to make it worth the effort.
Okay, I hope, Tomek, you are satisfied right now.
I'm more than satisfied, indeed.
Perfect. You might hold a record of the longest YouTube recording in the seminar history, as it's now close to 2.5 hours. But let me still double check. Do we have any more questions? Anybody still wants to discuss something, ask something? Mark, are you happy? Do you want to comment, or you have to unmute?
I am happy.
Okay, that was brief. Okay, so if Mark is happy, I think we had a very long day. So let us thank Frédéric again. Yes, thank you so much.
Thank you very much
for the talk.
Thank you for the opportunity.
And let me just briefly say before we end the session that in a week we are going to have a talk by Guillermo Cortinas from Buenos Aires about the K-theory of Leavitt-Pav algebras and the algebraic Kirchberg-Phillips problem. It looks very exciting. By now, Mark and I know the abstract. This looks really, really exciting. And please remember that we shift the clock next time. So in a week, Warsaw is going to be on UTC +2 time, not UTC +1 as it is today. So I hope to see you there. And for the time being, thank you so much for attending this talk and discussion. See you next week.
Thank you very much. Bye-bye.
Thank you so much. Bye-bye.